Okay, so I'm going to talk about mortality selection. I'm going to talk about this in the context of genetic studies. And this is done with a number of people, some of whom are in this room. So Dan is here, Amel is here, and Dalton should be here, but maybe he's gone missing. So let's see. So I should note, I am not a demographer, but I guess lately I've been playing one at conferences. And so I just wanted to tell you how I think about mortality selection, because it's kind of a simple version, but I think it's relevant. So on the left, I have a simple picture of what the true world is for some hypothetical scenario, where we have on the x-axis there's some risk factor, and on the y-axis there's some outcome, and there some outcome like some kind of disease perhaps, or cholesterol, something that is going to be bad for you. And there's a positive association between the risk factor and the outcome, right? That's the line with the positive slope, the association b greater than 0, right? That's what we would see if we had kind of the complete data that was not censored in any way. The idea I have about mortality selection is that for those that are high on the outcome, we're less likely to observe them because they may have died, and as a consequence, we're going to have reduced variability on the outcome. This is going to attenuate the observed association between the risk factor and the outcome, and we're going to end up estimating some association close to 0, right? So that's the basic problem I'm concerned about. So the ingredients of today's talk are really going to be polygenic scores, and polygenic scores specifically in the context of birth cohort studies. And so the reason I think this is interesting is that there have been a number of papers that have come out recently looking at how the genetic effects may be moderated by birth context. So there were 2 on BMI, and then 1 that I was involved with on smoking, which is how I actually got interested in this. Clearly, smokers are likely to die, and that was a concern in our study. And so this is really just a full look at this problem. I also want to do just kind of throw an advertisement up there. This is a paper that will be coming out next week looking at assortative mating and fertility as moderated by birth context. And so this is work by Dalton, Dan, some other people, and myself. So be looking for this.
Where's it come up?
PNAS. Okay, so here's the basic framework, right? I'm imagining some association between some genetic, some part of the genome, that's the G, and some outcome Y. So the subscript B there is to indicate that I'm imagining that the association is a function of birth year, right? This is non-constant over time. And I don't think it's wild to think that there's going to be some sensitivity to the historical context for some kinds of genetic effects. I mean, I was just thinking earlier, if you think about BMI, smoking, educational attainment, in the last 50 years that we've seen sea changes on all of these things, and you can certainly imagine cases in which the underlying kind of genetic architecture has changed as a consequence of exogenous policy changes and just the broader social changes that we've lived through. Now, it could also be the case that some genetic effects are relatively constant over time, maybe if we're looking at small windows, or if we're looking at very kind of biologically driven things, so maybe cystic fibrosis or Huntington's disease, some of these very simple Mendelian disorders, we probably wouldn't see this, right? And so in those cases, we may be interested in marginal effects, right? Effects that are kind of, basically we're just looking across time and not really thinking about sensitivity for birth cohorts. And so I'll actually, I'll make use of both these. This is, I think, the most interesting bit, but I'm going to talk a little bit about marginal effects. Okay, so what is the role of mortality selection here? Well, the basic problem, as I'm thinking about it, is that the estimates that we get of association between genes and outcomes may depend upon the window at which we collect data, which I'll denote by T, right? And so now I have an estimate of the association between genes and an outcome that is conditional upon the true effect is conditional upon birth year, but the estimate may be conditional upon the time at which you try to measure the association. And the issue is that we only observe those people whose year of death, which I'll use D to index, is exceeding the year of genotyping, right? So we only see those people who have lived up until the genotyping window. And so mortality selection is the fact that D is going to be less than T in a lot of cases. So when mortality selection is independent of G and Y, then missingness is at random, and we may not, be in bad straits, right? And this might be the case if development takes place prior to the age T minus B, right? So if you are looking at maybe some kind of, if you're looking at the genetics of, some kind of early life outcome, right? Maybe birth weight or something like that. It could be that the genetics related to, say, like Alzheimer's are not going to play a major role there, and that, mortality selection is unlikely, perhaps, to bias those kinds of observations. But if development is complete by T minus B, right? That's the age at which people are genotyped, then we're likely to be in trouble. And so I think that the easiest example for me is just the idea that if you're studying smokers and you're trying to look at old people to understand this association, you're likely to have lost a fair bit of smokers, right? They have this inconvenient habit of dying. And in particular, I'm concerned about the fact that reduced variation in the outcome is just going to lead to attenuation in this estimate, right? So we're going to end up observing an association that is potentially less than the true association, just due to mortality selection. Okay, so I'm actually going to try to see what happens when I look at this empirically. I'm going to use the HRS data. So this is, of course, the Health and Retirement Study. It's a nationally representative longitudinal sample of older Americans. The study started in '92. It's been followed up every 2 years since. Other people have looked at the problem mortality selection in this study, and they've found that it leaves the remaining respondents healthier, wealthier, and wiser, which is, I think, a pretty nice way of putting it. In 2006 and 2008, there was kind of this two-step genotyping process where some of the sample was genotyped in 2006, some in 2008, and so you obviously have to live until 2006 to be genotyped. I also just wanted to flag the fact that HRS is currently in the process of creating a polygenic score database. So that is, they're taking their genetic data, they're taking GWAS results of the kind that we heard Melinda talk about earlier, and they're creating polygenic scores for a number of things. And so I think there's going to be an explosion of research using those scores. And so I think that this type of observation about maybe the limits or the biases that are potentially problematic in the use of those scores is becoming more salient. All right, so in the HRS, there was really this kind of two-step process that you had to go through to be in the genetic sample. So the first step was that you had to at least live until 2006 or 2008, right? So that's the mortality selection part. We started with 37,000 people. Of those, roughly 7,000 died prior to 2006, right? So we lose about 7,000 right off the bat. Of the remaining 30,000, there was a second step that respondents had to go through. They basically had to elect, they had to be around, available, and then elect to be in the genetic sample. And so we lost actually 18,000 in that part of the process. So there are 18,000 people that we do not have genetic information on that were alive as of 2006. And so this two-step process is interesting. Ultimately, I'm left with only 12,000 of the original 37,000 that have genetic data, and I've lost them for two reasons, and that's a little bit messy. It turns out that both of the steps have implications for how long you live. So what we have here are survival curves for the three groups. So this line, this is the group that died prior to 2006. They died earlier than the other respondents, not surprisingly. This is the group that lived at least until 2006, but then are not in the genotyping sample, right? So they still die earlier than the final group, which is those people that we have genetic information for. So we have, evidence of mortality selection, evidence of longevity differences throughout here. But I'm really only going to focus on genotype versus not. So I'm going to model mortality selection because the bottom line is that these two selection processes are both interesting, but they're not tractable via the same models. We looked at this, and essentially what predicts living longer may not predict being in a sample always in the same kind of way. So I'm going to focus on whether or not you lived until 2006. That's the thing I'm going to try to model, and then basically ignore this other selection issue. I'm ignoring it kind of for the moment. I don't want to say it's not important. We know it's associated with demographics, for example, and so that's something we're going to try to account for in other ways. But I'm not going to focus on modeling that. So here is another look at the data. I've now broken things up with respect to sex and race. So we have the non-white females, non-white males, white males, non-white or white females. And in all cases, we just see that the genotyped respondents are living a good bit longer than the non-genotyped respondents. I'm breaking things up throughout my analysis by sex and race because these are salient factors in terms of who consents to being genotyped, right? So I'm trying to at least deal a little bit with this second selection process into the genetic sample via this kind of stratification. One last look at the data just descriptively. This is now the roll of birth year. And so we have the different HRS cohorts, AHEAD, CODA, HRS, war babies, and the baby boomers. And I just wanted to emphasize that the real kind of mortality selection issue is in the early birth cohorts. So the green and black lines here are the non-genotyped people. We have basically males and females, but you see that the non-genotyped males and females are dying before the genotyped males and females. And this is especially true in these early birth cohorts. The boomers just haven't lived long enough for mortality selection to really, kind of start to do some winnowing there.
So, sorry, I just want to make sure I'm clear. So, non-genotyped includes any reason for not being breeding?
Yeah, basically we just don't have data on you.
So whether they died too early or
otherwise not in the sample, yeah.
Okay.
Yeah, so it's a little bit tricky. Here I'm showing you kind of the whole story, and now I'm kind of conflating the two things. But I do model mortality not being in the genetic sample. Okay, so the two questions I'm going to try to address empirically in the remaining slides. First, I'll try to talk about how effectively we can model mortality selection, and then I'm going to talk about how we could use information from these models to maybe enhance the inferences we're making about genetic associations. Okay, just to motivate the models I'm going to look at for mortality, here are ratios between, so these ratios all show means for those who lived past 2006 as compared to means for those who died prior to 2006. And I have, the kind of usual suspects, education, and then a bunch of different health-related factors, so BMI, heart disease, smoking, depression, diabetes, heart disease, and Alzheimer's, and then self-reported health. And what you can see are differences that aren't kind of wildly outside of what we would expect. We see that those who died earlier those who lived at least till 2006 had educational means that were 15% higher than those who died prior. This is reverse coded, but this tells us that those who lived past 2006 were in better health than those who died earlier. Nothing shocking there. These are, I think, a little more provocative. We see big differences for depression, heart disease, and Alzheimer's, right? So, basically, for those who did not die prior to 2006, they had Alzheimer's at only 40% the rate of those who died before 2006, right? So these are very big differences, and I'm emphasizing these to suggest that we have kind of interesting variables for modeling mortality here. Okay, so this is a table showing results for our model's mortality selection. We have in the top row a set, so in all, these results are all looking at AUC. That's going to be my criteria for how I'm judging the effectiveness of my models. The top row looks at health only, right? So these are models based on only these health outcomes. And I'm able to predict a pretty decent amount of the variation separately in the white males and females in terms of mortality based on my model. So I'm modeling whether or not you died prior to 2006, and I'm doing a fairly decent job of it with just the health indicators. The second row I actually include birth year, and the predictive power, not surprisingly, jumps a fair amount. You can kind of gauge these numbers relative to an AUC of 0.93. There's a paper suggesting that for a perfectly heritable disease, for a heritable disease that you had perfect information on, you would see an AUC of around 0.93, right? And so I think that, 0.88 is not so far from that. So I think this is pretty decent prediction of mortality based on health indicators in the birth year. I then considered two additional models, models that included birth year interactions with all of the different health outcomes, and a random forest model, and these really didn't improve my prediction of mortality, right? So we're able to, predict about as well as we can mortality based on a relatively simple set of models. Any questions about this?
Do they have the death certificates of those that died? Do you have those, or are they? For the HRS, sorry, I was thinking so could you also look at people that had died that were in the sample, and don't they have traceable death certificates?
Yes, so do you mean
So cause of death?
Yeah, so I believe they do have that. We haven't used it yet, but I believe they do have that. Any other questions? Okay, so the punchline up till this juncture is that we can do a decent job modeling mortality. I don't, like I said, I'm not a demographer, so this was the first time I had ever done this, but I don't think this will be a shock to many of those in the room. Now, how can we use that to move forward, right? So the punchline here is that I want to kind of take stock of how sensitive my genetic association estimates are to the fact that I'm observing a sample that has already experienced mortality selection. So that's the goal. So I'm going to first show you that we can do a pretty good job of minimizing survival differences between genotyped and non-genotyped respondents based on my models. So what I have here, I have separately for white females and white males, a bunch of Cox survival curves. We start at 60 here. That was, I believe, the mean, that was the, I want to say that was the mean age at first interview. And we have survival curves separately for 1930 births, those are in black, and 1945 births, those are in red. But the more interesting distinction is between the solid and dashed lines. The solid lines, which are always higher, are the genotyped respondents, and the dashed lines are the non-genotyped respondents. And so the question is, can we reduce the differences in survival between genotyped and non-genotyped respondents by using our models for mortality? In particular, I'm just going to select those that are at a high probability for having lived until at least 2006 based on my model. And what we want to do is essentially just make the same colored curves closer together, right? And we can do this fairly well, right? It's not perfect, but I can get rid of a lot of the difference in survival based on taking those that look like they were going to live at least until past 2006, right? So this is just evidence that I can actually, I can get some kind of empirical traction on reducing the differences in survival based on my models. So now I'm going to adjust association estimates, right, via some weighting to make the average. Basically, I'm going to adjust the naive association estimates I get for mortality selection such that they become average treatment effects, right? And I'm going to compare those to just raw naive estimates. And I'm going to do this for a number of outcomes. So I'm going to look at BMI, height, education, and smoking. For all of these, I'm going to use genome-wide polygenic scores. So all of these polygenic scores are constructed with over 1 million Snips. I'm going to look at both kind of static, the marginal genetic effects, and then I'm going to look at the effects as they vary by birth cohort. And I'm going to look before and after inverse propensity weighting. Before I do that, I wanted to just show you these are the mean polygenic scores for my 4 different types of scores as a function of birth cohort. And you can see some decent changes, right? So we see that those born in 1920 have a much higher mean polygenic score for education than those born in 1950. Now, we're not observing a long enough time frame for this to be due to evolution or selection or something like that, right? This is just mortality selection. And we see this kind of across all of these. This is the biggest difference, but you certainly see kind of upward trends for several of these. BMI and height are a little bit different. The relationship that these have to mortality, especially in HRS, is a little bit complicated. But certainly for these things, I think you get kind of clear evidence for mortality selection. You have more educated respondents living longer from these earlier birth cohorts, and the people who were most likely to smoke from the earliest birth cohorts dying. Okay, so let's first start with the marginal associations, right? So these are just the main effects of the polygenic scores on the outcomes. These are, just the raw associations. I don't want to talk too much about the magnitudes. These are all, so a 1 standard deviation increase in your polygenic score for BMI predicts around 0.2 additional BMI points. They're all highly significant. I want to think about how these change in magnitude as I look at different types of estimates. So I first consider estimates that are weighted based on my 2 kinds of models. So I separately consider the model where I use health indicators and birth year, and then just the health indicators. And what you can see are changes that are, not huge. The changes are on the order of a few percentage points, one direction or another, right? So if you look at smoking, we see right here that the marginal effect on smoking of my polygenic score is maybe 4 to 5% smaller after I adjust for mortality selection. That's not huge, but I'm going to come back to these marginal effects later. I think the more interesting bit here is not the size, but what happens when I consider estimates from a sample that saw enhanced mortality selection. So what we also did is we looked at those who had died in HRS by the most recent wave, and we treated those as though we did not have genetic data for them, and then re-estimated associations. And across all of my different variables, I see changes in the association estimates that are counter to the changes I see after weighting, right? And so what I'm seeing here is after weighting, my marginal estimate of the effect of smoking decreases, but when I look in the enhanced mortality selection group, it increases, right? And so the fact that these things are in opposite direction relative to this naive estimate suggests to me that we really are kind of able to control for the effect of mortality selection. Okay, now let's look at the dynamic model. So now I'm basically interacting the polygenic score with the year you were born. I kind of unhelpfully removed one column from the table, so let me just tell you what these are. I have BMI, height, education, and smoking. The individual rows are the main genetic effect, birth year, the main effect of birth year, and then the interaction between the polygenic score and birth year. So again, the marginal effects are not that wildly different, and we do see in a number of cases kind of significant effects of the interaction, but I don't want to focus too much on those yet. I want to see how those things operate before and after weighting. So when I introduce weights, for BMI and height, I don't really see much differences in these interaction effects, right? These are changing, again, kind of 4 to 5 points. But I think that the story between BMI and height and HRS and mortality is somewhat complex. If you look at education, right, I'm getting a much larger estimate of the effect of education, of the education polygenic score on education after weighting, right? This is up by 19% or 12% birth year, and we see even bigger effects for smoking, right? So we're seeing now a much bigger upward trend in how the genetics of smoking are predicting smoking behavior over time after I weight, right? I'm seeing an estimate here that's 30% bigger. This is a pretty decent jump. I then again look in the enhanced mortality selection group. So again, this is a group where I take mortality up through the most recent wave of HRS and remove those people and treat the sample, basically compute a new naive estimate. And I see now, I think this is quite interesting, right? I see a huge drop in this relative to this naive estimate. So when the mortality selection is really operating in the kind of heaviest way I can get it to operate in this data, I get a very small estimate. When I try to account for mortality selection in determining the effect of the polygenic score on smoking behavior over time, I get a very different story, right? The estimate here would be about half the estimate here. So this is a pretty profound change. This one red arrow just suggests that we're not getting kind of a consistent change when I go from the weighted to the enhanced mortality selection. But again, height is kind of funny in this case, so I'm not making too much of that. But I do think that the fact that we very consistently see changes in one direction when we kind of weight to get average treatment effects that are corrected for mortality selection, and opposite changes when we kind of bake in more mortality selection. I think that's a very compelling story. All right, so a few conclusions. So first, how effectively can we model mortality selection? I think that we do a pretty decent job of reducing the discrepancy between genotyped and non-genotyped respondents in terms of longevity. And this information seems to be pretty important if you want to study kind of associations of genetics and outcomes, especially if you're interested in how these things might change over time. And before I quit, I want to talk about kind of two other things that are part of the story that I have yet to explore, but I do think are salient. The first has to do with additional issues related to selection. So it's well known, for example, that there are demographic effects and who consents to provide genetic data. So that's one issue. This is a study that came out a week or two ago that I thought was interesting, and this is a study showing, this is very similar to what Dan was talking about earlier, that those people who, that are in this particular study and that are interested, so this is a study from England, right, and it's a study that's looking at psychiatric things, and basically the punchline is that higher polygenic scores for schizophrenia were consistently associated with non-completion, right? So those who were most genetically predisposed towards schizophrenia were the least likely to be represented in this study, right? So this is a very different angle about selection, but I think it again shows that these kinds of genetic studies. So this suggests that genetics may kind of tell you more about who's selecting in your sample. My observation is that we need to be careful about who's in our genetic samples, but all this stuff I think just gets to the fact that we need to be concerned about selection in some of these studies. Finally, I wanted to come back to the fact that I'm not seeing huge effects at the margin. So if you remember, I saw changes here for smoking, which is the biggest one, of about maybe 5% after when I didn't correct for mortality selection. So that's not huge, but 5% is not nothing. And I think where this stuff might really matter is in the context of GWAS. And so just to kind of illustrate why I think this matters, I went back to the original GWAS for smoking. This is the 2010 Nature Genetics paper by the TAG Consortium. And they talk here about the TAG Consortium conducted GWAS across 16 studies originally designed to evaluate other phenotypes, for example, CVD and type 2 diabetes. So I then flipped through to the back and just looked at the 16 studies. Here they are. And I was interested in who was in them. The first study is Eric, right? And these people were between 45 and 60. This group wasn't very specific. They just said an older population. The third one is people over 65. And across the way here, you can see these are old people that quite likely may have died, and they may have died for reasons related to smoking. You even have, these are case control studies, right? And so these people are sick. That complicates things further. And I 5% is not huge, but when we're talking about millions of variants, I do think that, this is an important thing that you may not want to build into the GWAS design, but might be a kind of important thing to do as a secondary check on the quality of your GWAS results. So if you're, for example, going to look at HRS to kind of validate GWAS results, then you could certainly consider what the effects of mortality selection might be there. I'll stop there. The paper, if you're interested, is currently under review, but there's an earlier version posted on the bioRxiv, which you can also do. Thank you.
Yes, there's been a fair amount of the smoking work goes in different ways, right? Are you a smoker or not? There's been GWAS of when you started. One of the phenotypes of interest is this regular smoker idea, which is often 100 cigarettes in a lifetime. That sort of like counts as initiation. People are pretty good at reporting how many cigarettes they smoke. It's a nice quantitative phenotype that people recall. Retrospective recall of when you started smoking, again, is pretty okay, ballparking it into years. The genetics of smoking, though, have been interesting. The GWAS of whether you smoked or not were not successful. They didn't find any hits. The GWAS of smoking quantity were more successful. They turned up a half a dozen hits in nicotine receptor and nicotine metabolism genes. So that was great. And then everybody went home. We haven't heard from them since 2010. The whole genome polygenic scores, though, the findings have been sort of opposite, where if you want to predict smoking behavior in an independent sample, it's the polygenic score trained on the ever smoker phenotype that seems to be more predictive of variance in behavior than the quantitative Packyer's phenotype that proved to be more successful at identifying specific genes. I'm not exactly sure what to make of that, but it's an interesting story.
And one more thing in smoking I want to ask is, how do you determine the response across regions? Because at least if you see, historically, like European smokers versus Japanese smokers, is there a difference in the patterns you observe, or do you not see a regional thing?
By regional, do you mean national? Like
national. I'm not quite sure how to phrase the question.
Yeah, I have no idea. Good question, but I have no.
The GWAS are all of white people.
Yeah.
Okay.
I wanted to ask whether we know something about non-compliance or refusal to submit, which you mentioned, and it came up in the schizophrenia article, I guess, there at the end.
So certainly there were people that refused to give genetic samples in the HRS. That was definitely one reason that people ended up in this kind of middle band of people who had lived long enough but who didn't provide genetic data. This is a really complicated group. It's just a real mess. There's a few people that came on in the most recent refresh that weren't in there. There are people that just fell out of contact, people that didn't provide samples that weren't of sufficient quality. So that's part of the reason I'm not trying to model that aspect of selection. It's just a really nasty issue. I don't know, that's not a great answer, but
I don't have one myself. When I present stuff on biomarkers to people who are interested in inequalities, what they'll say is, well, don't you see differential, sampling rates across race and socioeconomic status?
And so certainly that's why we did everything kind of split by race and sex. We only really have sufficient genetic samples for we only really have sufficient samples and good polygenic scores for the white respondents, which is why I showed association estimates for those groups. But we did try to get at the fact that you see kind of demographically informed non-consent rates by splitting things, at least in this way.
So in the HRS, like other data sets, less well-educated and non-white participants were less likely to consent to being included in the genetic sample.
And I think they've developed weights that try to correct for that, but whether they do or not is not clear. But maybe Kathleen has some insights about this too.
Weights for correcting for.
Well, so you get the sample, and then you might want to rebalance, according to what consensus tells you you ought to be seeing.
I mean, so we do that on a wave-by-wave basis, but for the collection of like the biomarkers.
The biomarkers,
So we
yeah.
don't, yeah, I mean, I think that some of the other, I mean, we fortunately have compliance rates of like 96%, but I know other studies, like MIDAS has specific biomarker weights, yeah.
Yeah, so does HRS, I believe.
Yeah, that's right, yeah.
In your summary of the other stage of selection from those who survive at the age of genotyping but are then actually genotyped, in your summary survival curves, you didn't show this condition on age, but you have, I believe, studied whether conditional on surviving to be genotyped, there are later mortality differences from selection into genotyping. Would you
Yes.
like those?
Yeah. So that's
I
right.
think are
I had that slide in until a few days ago, and then I cut it out. But
important things for
Yeah.
this community to know.
Very true.
Could you
So-
say a little about that?
essentially, what's the best way to show it? If you look at these Cox curves, again, this is, these are, if you just look at the black curves, we essentially have survival differences for genotyped and non-genotyped respondents. If I then condition on only those who lived until at least 2006, you see much smaller differences between them. They would fall within each other's confidence intervals at that point. They're not nearly as large. So it is, what we're picking up is definitely mortality selection here. Excellent.
So, a couple of questions. The first is, what happens if the genotype affects the phenotype that affects whether you're likely to die?
Yeah, sure. So
That's precisely what we're concerned about.
yeah, that's exactly that. So if genetics
So-
make you smoke,
you've demonstrated a bias. I'm just thinking about the next step, which is, can you correct the estimated coefficients for?
yeah. So I think So let me talk a little about this. So
Yeah.
so there's this old observation that at least in the U.S., recent smoking behavior is much more dictated by biology than smoking behavior in earlier birth cohorts. This isn't shocking if you just think about the fact that if you were born in 1920, everybody smoked. If you were born in 1950, you were choosing to smoke in a very different kind of paradigm with respect to health and information and all these things. And so that's kind of where we picked up. So we started with the observation that in an original study, we had focused on this and the fact that basically we saw some evidence that the polygenic score was better predicting smoking behavior over time. It was better predicting in later birth cohorts. But we were concerned about the fact that we were quite possibly missing a lot of smokers from our sample because they had died. And we argued back and forth about which way the bias might go here. I ultimately kind of come to the belief that this is probably downwardly biased. Your concern is exactly, I think, what we're trying to address. It's just it's a messy situation.
Yeah. So it depends very much on the
And I think
variable in question.
I think that's exactly it. So the reason you're not seeing stuff here for BMI and height is because I think for those phenotypes, mortality selection is largely orthogonal to the association between BMI, as observed in HRS especially, and height and the genetics that underlie them.
So one final question is, suppose you looked at, say, the variances at age of death, between smokers and non-smokers. Presumably, you would see a higher variance
That's a good question. So one thing we have...
in non-smokers than in smokers?
These are smokers who survived at least to age 50 and on average to age 60.
Yeah.
So,
and if the effect's 5%, how much do you expect? Do you think? I have no experience in this. That's why I was asking. Maybe you worked on this for a long time. Maybe you have any prior expectation on what you'd expect these differences to be.
Well, you don't see any with education and income. You don't see much. Certainly not, that size. But I don't know about smoking.
I don't have a great answer. We did look at the variation of the polygenic score as a function of birth cohort, and you don't really see much.
Yeah.
To the extent that you see changes in the variance, you don't see it in the coefficient of variation, right? So it's explained by changes in the mean. So I haven't looked at exactly what you're suggesting, but I'm not. Yeah, we did kind of walk in that direction a little bit.
Yeah. Right, we'll start with our next one. Yeah, so this thing is the pointer.
All right. Okay, thanks. Yeah. So, I'm Sid. I'm going to be talking about my paper with Tolja, David, and Mark Feldman. And I've changed the style of this paper a little. It's designed to address some of the points which David and Ken have raised in a recent document. So it's going to kind of work in reverse order. You're going to hear some stuff and then why I'm talking about it later. So for now, you just got to deal with it. But yeah. All right.
No motivation.
So the question I'm analyzing is one of the oldest questions in genetics. So what is the percentage of variation in the trait, which is VP, can be explained by the additive genetic contribution, which is VA. This is commonly phrased the narrow sense heritability, and you have VA over VP. Now, in the past, we didn't have genetic data, so what was done is you used to plot the mid-parent phenotypic value and the progenitor phenotypic value and draw the regression line. And the slope used to give the heritability. Now, this is the case of height, and the slope is about 0.67. Now, in the 2000s, what happened was we started collecting a lot of genetic data, so we were in the position to ask, can we compute the heritability directly? And when we use the genetic data, using the initial approaches of association studies, we found that we're not able to explain a very large percent of the variation. So as you can see here for this study, they were able to explain only about 3% of the variation. So the heritability is about 0.67. We are able to explain 0.03, whereas the remaining 64%. So this was essentially the missing heritability problem. And in 2010, one of the groups, a group from Australia, claimed that they had solved this problem, at least partially, where they said, the problem is not that the heritability is missing, but it's actually hidden. So what you do in association studies is you use very stringent p-value criteria to filter out the Snips. And they were saying when you use these stringent criteria, what you're doing is you're leaving out a lot of the Snips which are making somewhat moderate contributions towards the phenotype. So in their studies, they commonly find like heritability is about 50%. And this is about a 10-fold improvement over what traditional methods used to provide. I started looking into some of the results. A lot of them began with the work of actually Jason and Ben. And I've been trying to convince Ben to market his paper a lot better, so hopefully by the end of this talk he does that too. But so let's just get into the data. I'll show you why. I mean, the reasons will become clearer as I go on. So this is the data. This is the standard stuff people have spoken about so far. We have n people, p Snips. The phenotype is an n cross 1 vector, which I'm going to call y. And the genotype matrix is z, which is an n cross p matrix. So you have n people and p Snips. For each person, you have values of p at p single nucleotide polymorphisms. And this matrix has been centered in scale. And generally, typically what we have is the number of Snips is much greater than the number of people used in the analysis. So you have a couple thousand people and about 100,000 or maybe 1 million Snips. So this is the typical Gcta model. The model is assuming that every SNP makes a random contribution towards the phenotype. So here, the vector u, which is a p cross 1 vector, is describing what the contribution of each of these SNPs is. And since you have p SNPs in our analysis, each one is making a contribution of sigma square. The total contribution from all the SNPs is going to be p sigma square. And the variance in the phenotype you can compute to show is p sigma square plus alpha square, and that is commonly scaled to 1. So you have the heritability then given by additive genetic contribution Vg over Vfen, which is p sigma square. Now, there are a few points which I want you to note here. This model is precisely specified. This says, this is stating all the assumptions you need to know while doing the analysis. So when we submitted our paper and stated this model out, the authors of the Gcta... Right in time for the spooky tune, I know. Yeah.
That was a setup.
So, okay, what was I saying? Yeah. They said, like, the actual assumptions are that we're assuming that the SNPs are in strong LD with the causal SNPs. And that's precisely what we're assuming in Gcta. But if you see this model, you need to encode that information somewhere here. If you don't encode it, the information is not relevant. A couple more things to note. Here, we have information on n particular people and p particular SNPs, but we're getting information about a very global phenomenon, which is heritability. So you're using local information on a set of people and SNPs and getting information on the entire population. If I were to tell you that the heritability is, the estimate is 0.67 and the standard error is 0.03, you're not automatically going to assume, well, of course we took the people in this room. You're going to assume it's a random set of n people which you've chosen in your analysis. Okay, so what the authors in Gcta noted is that we're only interested in p sigma square. And so why keep track of p at all? Why estimate sigma square and then multiply by p? Let's just estimate p sigma square directly. So what they do is they reformulate the first term in this expression, and they get y equals g plus epsilon here. Where again, now you'll see they replaced the sigma square by this vg, which was p sigma square, which we needed before. And we get this new matrix A, which is called the genetic relatedness matrix, which is 1 by pz transpose. And this matrix is describing the relationships between the n people. So the ij entry of this matrix is the relationship between person I and person j. Now, a few points I want you to note about this analysis. After this setup has been made, the role of p has been completely removed. Okay, and for every GCT analysis, what you do is you provide this matrix A as input, and you get a heritability estimate and standard error as output. We don't know what SNPs are being used in the analysis. And now, what is the insight into doing this? So, to get a better understanding, let's suppose that for the people I'm concerned with, the n people I'm concerned with, we knew all the SNPs. So M comprises all the SNPs. There are k of them which are causing the disease, so we'll call them causal SNPs, and the rest, k plus 1 through M, are the non-causal SNPs. So the GCT analysis essentially is stated as follows. They say if we knew the k causal SNPs, then our model is going to run fine. We're going to use only the causal SNPs to estimate sigma square, and then k sigma square is going to be our heritability, and everything is well and good. The problem is, in reality, we don't get only the causal SNPs. In fact, we don't even know what SNPs we're using. We don't even know what the value of k is. So we get a random subset of p SNPs. So to account for this fact, what they do is they say that we are going to assume that the variance, the effect of just having the causal SNPs is approximately the effect of having any set of SNPs. And this is the central assumption which Gcta is making. Now, the question is, does this assumption hold? Before I get to that, we need a method for comparison here. Now, since the number of SNPs can vary across different studies, how do we compare the various studies? Now, if one study is using p SNPs, then the model is going to be estimating Vg, which is p sigma square. But if the model is using q SNPs, then it's going to be estimating in q sigma square. Now, since p is not equal to q, it makes no sense to compare these two things. So what we should be doing is, in fact, comparing sigma square. And this is not very difficult to do. I'll just show you how it's done by a simple example. So this is a standard Gcta output. Now, note here in this output, they don't even mention the number of SNPs used in the study. Because in their opinion, in their framework, this is actually irrelevant. Because you have causal SNPs, you have non-causal SNPs, a mixture, whatever it is, the heritability estimate and standard error is going to be always the same. So I mentioned the number of SNPs over here. So it's 50,000 SNPs. Now this is the heritability estimate and the standard error. So the standard error of sigma square is going to be basically the standard error of the heritability divided by 50,000. And that's going to be that. And the estimate of sigma square is going to be the estimate of heritability divided by 50,000, which is going to be that. All right. So now the question arises, is this method working as proposed or not? So this is one of the places where I really found a problem. So this picture is taken from the initial Gcta paper. This is the Yang 2010. So on the x-axis, he's plotted the proportion of SNPs used to estimate genetic relationships. That's percentage, which I marked perc. On the y-axis, he's plotted the estimate of variance explained by genome-wide Snips, which is essentially the heritability into perk. Now, the trait he's considering here is height. So the heritability is about 0.6. So we expect, and the blue bars here are his estimates of heritability. Now we expect the slope of this line to be about 0.6, which is about 30 degrees. And as you can see, the slope of this line is approximately 0, which means what you're finding is that the heritability estimate is essentially independent of the number of Snips used in the analysis after a point. So what the red bars here are a correction they propose to their genetic relatedness matrix, and they say that this correction actually improves their model. In fact, in their paper, they're actually proud of the fact that the heritability is independent of the number of Snips used in the analysis. This is one fact we are still fighting over in our ongoing battle with the group, but I'm too stubborn to accept I'm wrong. I'm not, so it doesn't matter. After the correction, what they find is that essentially the slope is always 0. So this was one of the serious red flags and why I decided I need to look into this model in more detail. Another result, actually, and this was the primary motivation, comes from the draft from Domingue and Boardman. Now, if you see, so what they do is they say, we are going to take our entire set of Snips and randomly start throwing out bunches of Snips. That's what they do here. So this is the number of Snips removed. There are total 250,000 Snips. And so he first rules out 20,000 Snips, then 40,000, 60,000, 80,000. And so if you see for the college, there's one line there and one line over here. The line which is falling steeply is him throwing away the most significant Snips. So as you can see, for the same level of number of Snips thrown away, the heritability estimates are drastically different. For instance, here. It's almost 0 for about 25,000 Snips thrown away. It's about 0.6 at the same level. So this was another thing which threw up a real big red flag for me. And the question arises, well, how many Snips are actually contributing towards my trait in some sense? And the answer is, it's probably a couple thousand Snips, which is actually doing most of the heavy lifting in our case. Okay, so let's look at, so there definitely was a problem. So I said, well, how am I going to analyze this problem? Now, the only input which is going into Gcta is this matrix A, which is 1 by PZZ transpose. Now, the key thing to note here is whatever the number of Snips I use in my analysis, the GRM is always going to be n cross n. And different values of P are going to produce slightly different GRMs. Now, what Gcta is assuming is that if I have a set of Snips and I compute the GRM, that is all I need. And so I asked the question, well, and by some guarantees in the central limit theorem, they say that the errors in the entries of this GRM are probably going to be small. So I asked the question, do these errors actually make a difference or not? And turns out they do make a big difference. So the question is, how are we going to quantify these changes? Now, A is a symmetric positive definite matrix. So it can be quantified in terms of n numbers, called eigenvalues, and n vectors, which are called eigenvectors. And we know a lot about these eigenvalues and eigenvectors. Now, in our paper, I've made a lot of emphasis about the matrix A, in some sense, being random. And the reason I do that is because we do not know which n people are chosen in our analysis and which p Snips are chosen. Now, there's one point which I'll get to later, which is that even when the number of Snips used is the same, you cannot condition on the matrix Z, because conditioning on, do you have a, okay. So please stop me if you have a question midway through, by the way. So if you are conditioning on the matrix Z, which you are doing in all of their analysis, what that's essentially assuming is that you're fixing the people and the Snips used in the analysis. So the heritability estimate you produce would be if I got a new set of people who had the identical Snip values at all of their loci. And only for that case will the heritability estimate in standard be valid. Okay, so this is just a quick show of the equations. So this is the log likelihood of the data. That's the log of the probability of observing your phenotype vector given the parameters, and is given by this expression, where C is alpha squared into the identity matrix plus VG into A. And what Gcta is doing is it's solving dou L by dou sigma square equals 0. And we show that, the first term does not depend on the eigenvalues and eigenvectors because there's no A there. These last two terms do depend on the eigenvalues and eigenvectors. So we show that the second term depends only on the eigenvalues of A, and the third term depends on the eigenvalues and eigenvectors of A. Okay. So at this point, I just want to make one thing clear. When we do our analysis, the only thing we're concerned with is what happens when a different set of people and Snips are used. None of our results are concerned with, are there numerical errors or not in some form or the other. If numerical errors pop up, it's fine, but that's not really the focus That's not really the focus when we do our calculations over here. So I'm going to be talking only about one case. Yes.
So can you go back to slides?
Yes.
What are you drawing from to get to formula like it?
Okay. So when you have the y equals, so the formulation with Gcta gave, you can show that the formulation forms the multivariate normal distribution. And so this ends up being the likelihood for the multivariate normal. I'll just go back a few slides. Sorry. Where did that go? So it all comes from this equation. When y equals zu plus epsilon, if u is normally distributed, epsilon is normally distributed, y will be normally distributed. So then I would say, well, what is the log of the probability of observing y given my parameters sigma square and alpha square? And that's the expression I get over there.
And the sample that you observed?
Yeah, so the sample is, we have only one sample in this case because we have only one phenotype vector. Y1 is a vector over here. And we have only one observation because you have whatever, say the heights of 40 people. And we don't have, in this case, the same genetic matrix and the heights of 40 people having the same set of genes, So that's essentially what we're trying to solve over here. And then what they do, the second term turns out to be a function of only the eigenvalues, and the third term is a function of the eigenvalues and the eigenvectors of A. Okay, so I'm going to be talking only about one case here, and that's the case of population stratification. This is a case which is widely observed in all populations. And the case is basically the following. Now, in Gcta, they assume that the allele frequency of all individuals are the same. That is, everyone is drawn by tossing a coin with the same allele frequency set. Well, what happens in natural populations is that they're not drawn from the same population, but is drawn from a mixture of populations like this. So instead of getting all A's, you get A, B, C, A, B. And when you get a mixture of populations like this, the eigenvalue distribution of the GRM A is extremely skewed like this. But what ends up happening is you'll have a few large eigenvalues and thousands of small eigenvalues. So when we presented this result, a lot of people got excited and said, well, you think the problem is unstable because the eigenvalues are all small. That's not why we're saying the problem is unstable. We're saying the problem is unstable because when you have a few large eigenvalues and a lot of small eigenvalues, the small eigenvalues are bound to have a lot of error associated with them. Now, for another perspective of why this is the case, think about what you do in principal component analysis. You take the top few eigenvalues, the top few loadings, and you choose only those. So in some sense, what you're doing is you're forcefully setting all the smaller eigenvalues to 0. You're forcefully eliminating the errors associated with all of them. In this case, you're not setting anything to 0, so all of those errors are going to remain intact. And so that becomes part of and so that causes the problems with the eigenvalues. Problems arise with the eigenvectors because these eigenvalues are packed close to one another, and there are errors in their values. So again, the eigenvector in one case and the eigenvector in the other case are going to be slightly different. Yes?
I ask a quick point of information.
Sure.
When you compute the genetic relatedness matrix,
yes,
GRM, have you standardized the variance of the columns as Yang and others do? So the columns are each of variance 1, or are these from unstandardized?
No, these are all. So I've done the standardizing to variance 1. These are not 0, 1, 2. Yes.
These are with the standardization.
Yes.
And you still get a 10 to the 18 factor.
Well, if you think of the covariance matrix.
Just a point of information.
Yes.
We can discuss later.
Okay. Okay. So if I'll just specify a point as to why. Yes, they are standardized, and you're guaranteed. Okay, all right.
And can I actually then just ask one other question?
Okay. Yes.
So, of course, there's one eigenvalue which is 0.
Right.
So have you thrown that one out?
No, I have not thrown that out. There's no reason to throw that out. I am finding an eigenvalue distribution. So I have not thrown that one out.
Okay.
I just found.
So if you were to remove that one, what would
then you get a couple thousand it's a couple thousand. The condition number comes to a couple thousand if you throw that away.
But since that eigenvalue is really 0, shouldn't you be saying that that ratio is infinity?
It is no, because this is a computed value. This is not
computed, but that's just numerical. You say you don't care about numerical errors, right? So the value is really infinity. It is
okay, so it's a lot worse than I'm pointing out then. So
The important piece of information you've just given us is that when you take that out, it's about 2,000.
right.
And these are on eigenvalues, not singular values.
Oh, my bad. So this is. I was talking about the condition number of single values, not of eigenvalues. I'm sorry. It's about 2,000.
Singular values.
Yeah, I'm sorry. I got confused because I'm presenting in terms of eigenvalues here. I apologize. But
this little set of technical groupies back here.
I'm sorry. Yes. I want to point out. I want to emphasize the point that there is no reason for us to throw away that last item. Never mind. We'll discuss that later. So. Okay. And so the gist of our analysis proceeds as follows. We make small changes in A. These cause large changes in the eigenvalues and the eigenvectors. And these cause large changes in the maximum likelihood estimate. And so what we essentially want to show, we show theoretical claims. I mean, we prove some results, which basically show there is possibility for why this can happen. And now we demonstrate this. We also demonstrated this numerically. So for our numerical demonstration, we used the Framingham dataset. That has 2698 people and about 50,000 Snips. So what I did is I used this entire dataset, and for the phenotype of blood pressure, I computed the estimate and standard error for the entire population, for the entire genotype matrix T. So I get an estimate and standard error of sigma squared T. Then what I did is from this set of 50,000 Snips, I kept sampling 5,000 Snips at a time, maintaining all the people, and I constructed 2,500 matrices S1, S2, up through S2500. And then I computed the estimates of sigma square S1 through sigma square S2500. Now, the question is, what relationship do I expect between sigma square T and sigma square S1, sigma square S2, all the way through sigma square S500? Sigma square S... Indian tourists are kicking in, sorry. Sigma square S2500. So we expect the results to be exactly the same. It's because, as far as Gcta is concerned, we are providing it with a 2698 by 2698 matrix, which is describing the relationships between those people. And so we expect the estimate and standard errors from all 2501 cases to be precisely the same. We, in our analysis, give a Gcta the benefit of the doubt, and we say, okay, let us just compute the 95% confidence interval using just the total population, and let's at least see if these other estimates lie within it or not. What we find is the red arrows here are describing the 95% confidence interval, and the histograms here are describing the values of sigma square. The histogram is describing sigma square S1 through sigma square S2500. So what you find...
How did you sample the Snips, the 5,000?
Randomly.
So they're random draws?
Yeah, they're random draws from... Because the thesis we're going after here is that variance of y given the causal Snips is variance of y given whatever p Snips you have. And what you find is most of the distribution is lying outside the 95% confidence interval. So when we sent this result to Yang and group, they were pretty pissed off. And they said, well, our model would never do such a thing. Well, it turns out it does. And this is from their paper. This is Lee et al., which is, by the way, if you're looking for mistakes in Gcta, this is my favorite one. So please go through it carefully. Here you see he's chosen 21,000 out of 300,000 Snips. And the same set of cases, same set of controls. And here's the 95% confidence interval for sigma square using the first one and the second one. So they are not even close to one another. So this shows that the problem, that there are real problems with the Gcta estimates. Now, let's go for another case. What if I use different sets of people but the same set of Snips? Now, when I use the same set of Snips, I can compute the heritability estimates directly because I'm going to be doing essentially H squared over P, and P is the same in both cases. Now, here is the heritability of bipolar disorder, where he's using, where they're using about 1 million Snips in their analysis. Okay, and so here you see for the subpopulation 2, the 95% confidence interval is between 0.3 and 0.58, and for subpopulation 3, it's between 0.61 and 0.85. So they're not even overlapping 95% confidence intervals. So this shows an important point that even if I maintain the same set of Snips, it's not okay to, yes. Oh, sorry. Okay, yeah. It's hard to tell if it was a question or not. So, trying to whack me. But yeah, so, yeah, okay. And so this shows that you can't condition on the matrix Z even when the set of Snips is the same. Because, yeah, all right. And now this is another last slide from Domingue and Boardman, which I think is really important. What they do here again was throwing out bunches of Snips. And what Ben was finding was that you get this consistent heritability of 0.5 even when 150,000 steps were removed. And the line is almost flat over there. But at this point, if you look at the estimate of sigma square and standard error, the 95% confidence interval comes out to be between 1.96 and 2.04 into 10 power minus 5. But over here, the estimate of sigma square is about 5 into 10 power minus 5. So it doesn't lie within the 95%. So even though it looks like the heritability estimate is nearly the same, the number of Snips really matter. So the heritability estimate can be a very misleading quantity to look at. So, okay, now I want to make one last comparison to linear regression here. Because people said, like, look, in linear regression, you're conditioning on the matrix Z, which you use in your analysis, and this is the basic linear regression setup, where the estimate of error is given by, yi, which is the phenotype minus the estimated mean value whole square. And the key here is not in the computation, but in the implementation. What you do in linear regression is when you're trying to make a forecasting error, you include for a fact that we do not know where the new samples are coming from. And all linear regression text, you're going to find statements of the form, the estimate of PE, which is the error I just showed, by fitting ordinary linear regression, because it's going to map the idiosyncrasies of the original sample D. And this is precisely the problem which is happening in Gcta 2. So, okay. So on that note, thank you. Yeah.
Do you do any simulations to explore the space where you vary the linkage between the Snips? Because I thought that their correction was all based on assuming that the linkage in their observed Snips was the same as the linkage between the observed Snips and the unobserved causal Snips. And intuitively, it would seem that your critique is highly dependent on the extent to which the Snips are providing independent information vis-a-vis the causal Snips.
So that's what they say there.
Like
No,
I
totally agree with what you're saying. That's what they say that their assumptions are. But then when you are stating a model, you have to say what is going into the model. If you think about what information we get into Gcta, we get a bunch of Snips. Every time a Gcta estimate is reported, you say the heritability is 0.02 and standard error, whatever. You don't know what Snips are used in the analysis. And in theory, you're absolutely right for not reporting the Snips because they're supposed to be irrelevant. So the whole point of our paper is that P is really relevant and you just can't throw them away. So.
Well, I get that. But I'm asking is it relevant to more or less degrees depending on the linkage structure? I would assume that's the case. And you could explore that.
I think the Speed and Baldwin paper from AJHG looked at that and found the performance of G. What's that?
The lead paper?
No, the Speed and Baldwin paper. And found that GCTA performed kind of as you would expect under certain circumstances. But I don't know, maybe you guys.
Well, we can return to that. You had a question? No? Okay.
That's not it. saw that there. And
Well, thank you, Tolja, for inviting me. Okay, so this is joint work with Ken Wachter and Andy Dahl, who's in the back, also just came over from Oxford. So I'm going to say some things about the statistical theory underlying Gcta and related models, and it was inspired quite a bit by the work that Sid and Tolja did. We came, yes, and David and Mark, we came to rather different conclusions, but at least we managed to get the same notation, which is actually, I think, quite an accomplishment. So, so we're working in. Most of the letters here should mean sort of the same things that they did in Sid's talk. So we're talking about a model which is it's a high-dimensional random effects model. And so I first learned about this model from Ken a number of years ago, and I didn't think it was particularly interesting at the time, just because it's just a random effects model. I guess I know what's going on. But it turns out there are some interesting issues that arise because of the high dimensionality of it. And I mean, I think these are well brought to light in the work that Sid was talking about. So Z is an N by P genotype matrix, and we assume that the column variance, so the variance for giving the variance per site is normalized to be 1. It's actually, I've asked people why this is done. It seems actually, in some ways, like an odd choice, because it means that heritability in this model does not mean what heritability usually means. But anyway, this is a standard thing. It doesn't really affect, I mean, one could just as well do it with a different normalization or no normalization, but it does make a few things easier to analyze. So why is a phenotype matrix? For purposes of this talk, we're assuming that actually R is 1. In principle, we could be, right, often want to talk about multiple phenotypes, and that certainly fits in this context, but we're assuming actually Y is just a vector of measurements on each individual. And U is an unobserved P by R, but for our purposes, just a P vector of random effects, giving the contribution of a unit change inside J to the trait. And we assume, again, these are normally distributed with expectation 0. I'll talk later about what happens when we make changes to that assumption. And epsilon is an independent noise term, giving all the effects which are not genetic. And again, assume normally distributed and independent. Okay, so this is again what was in the same thing that Sid had. I found it convenient to express this for some purposes in terms of parameters that I call theta and phi. So theta is the noise precision, so 1 over the variance, which actually disappears from all the analysis. And phi is the ratio of the genetic variance to the noise variance. And then with the normalization constant P giving you the contribution of each SNP, right? So phi over theta is the total genetic variance. And right, so that's just what I'm saying. Because of the way we normalized the genotype matrix, we get that. So the narrow sense heritability, as usually defined, is phi over 1 plus phi. And I'll sometimes be talking about h squared as the as a parameter, and sometimes phi when it makes things a little simpler to write down. We have the genetic relatedness matrix as before, and the assumptions turn this into a multivariate normal model where with this covariance matrix, and we use the way these sorts of things are usually analyzed is in terms of a singular value decomposition of the genetic relatedness matrix, which essentially means that we're looking for a way of writing it that makes the contributions independent of each other. Okay. And then the terms SI are giving the size of the contributions. So what that means is that if I create new variables, so I take this matrix that comes out of the singular value decomposition and multiply it, this U, right, and multiply it by my phenotypes. So I basically create new linear combinations of the phenotypes. That gives me n new variables, which in principle I could have observed. That could have been my observation. Then these Zs are now independent variables. So they're independent observations, right? We've removed all the correlation from them. And they have different sizes now. And they're ordered. We order them with from largest to smallest. And the size of them, they're normal with those variances. Okay. So phi, this parameter which gives me the relative size of the genetic variance, is essentially telling me how different these Zs are in their size, right? So I have Z1 through Zn, which now no longer correspond to n different individuals. They are mixtures of all the phenotypes, and instead they are now independent and with sizes that vary. And the bigger phi is, the more different they are in how big they should be. Okay, so we can do maximum likelihood estimation. I'm not going to make a big deal about it, but I disagree with Sid about there being any problem with this estimation problem. Because when you have small singular values, they basically make small contributions, and I don't think there's actually any problem there. You can eliminate theta from the problem, and you end up with what we call a profile likelihood, which just means a one-variable version of the likelihood where you've eliminated the variables that you can solve for. And it turns out to have a very simple form, which is actually quite nice to work with, and you can kind of look at it and understand what it's saying. Right? So if we define these two combinations of phi and the observations, right, which I call W and V, then this is just saying that W and V have zero covariance at the solution, right? So what this is saying is, right, so think about at the true phi, right, these Zi squareds, have variance 1 plus phi sigma I squared, right? So if I had the true phi, then all those variances would be 1. And well, that's why, and so there's zero covariance because they all have the same distribution, and so they have zero covariance with this function that depends on SI squared. So essentially what we're doing is we're trying to find the phi that matches these components, matches the variance of these these rotated variables Zi with the variance that they should have. Okay, that's essentially what the problem is. I'm using, by the way, there's sometimes a bit confusing. I'm using covariance and variances here to simplify. We have two sequences, and we're talking about their empirical covariance as pairs of numbers, and that's different from. These aren't being thought of as random quantities. These are kind of fixed sequences, and they have a covariance or variance. So you can compute bias and variance, and actually this is a bit of a stone soup kind of thing, because this is what I was originally starting out trying to do, and at least from my point of view, I think the answer ended up not being all that interesting, but it actually threw up a lot of new questions, which I'll talk about later. But here, let me just say what came out of this. So if we look at the phi variable, if we were trying to estimate that, and I guess it's sort of the same as when you were talking about estimates of sigma squared, this may be one point, right? You can get a very large bias if this tau2, which is the variance of this wi, this combination 1 over 1 plus phi times these singular values, is small, which it often is. If it is often very small. I'll talk about that in a minute. So you can have quite large biases for pretty large values of n if you're trying to estimate phi. But this isn't all that interesting, right? The point is that phi is, I mean, if you think of it as a function of the heritability, it's one, right? It's phi over 1 minus phi, which is a very skewed function. So if you take an unbiased estimator for a parameter, and you just take a skewed function of it and compute the bias, you will get a big bias out of it. So there's nothing odd about that. On the other hand, if you look at at h squared, right, that bias actually is in most circumstances very small. It's a small negative number because this 1 minus w bar minus h0 squared is typically small and will tend to cancel out the tau2. So there isn't much bias here in estimates of heritability. Yeah.
Did you say tau2 was small?
Tau2 is small, but 1 minus w bar minus h naught squared will typically be also very small.
Okay.
It's also a small negative number.
Okay.
So so the bias actually tends to be a little bit downward, but again, small. Now, when I was first told about this model, actually, I kind of immediately thought of it as a regression model, and so let me just explain in what sense it is a regression model. I've rewritten the variables in this form, and so we can we have these, we can think of it, Zi squared are our observations. They're not the way we originally made the observations, but we've recoded our observations in these Zi's. And these can be thought of as being equal to standard chi-squared variables multiplied by these numbers that depend on phi. And so if I take logs of that, and so I get this equation, and if the singular values are close to 1, which in many cases they mostly will be, then we can approximate that in this form, which is exactly like a linear regression model. if we were trying to predict zi squared, log zi squared from si squared, right? Si squared are information we have from the genotype matrix, and right, that's the intercept. H squared comes up as a slope, and that's the error term, which is, except it's not a normally distributed error, it's a log chi-squared distributed. That's the log chi-squared density. So this Gcta model can be thought of as really being just a slightly oddly formulated linear regression model. And that raises some interesting issues because, oh, sorry, okay. So first of all, here's what it looks like if you plot these, look at this as a linear regression model. So these are, I just simulated for 100,000 Snips and 4,000 individuals, and so I've just plotted the log z squared against si squared. You can see there's very little information here, actually, right? There's a huge scatter for each point, and it's actually kind of amazing you can figure anything out about what the correct slope is, right? I mean, I've plotted two different lines representing, slope, h squared equals 0.5 and h squared is 0.33. And, compared to that mass of points, they don't look very different. But in fact, you can pick it out, but this is why you get this, 1 over n tau 2 in the variance, right? So tau 2 is the variance in the si squared, and if you don't have it, you need either big N or big spread in these si squareds in order to be able to pick out what that slope is. Here's that same thing blown up just in the range around 0 to 1. It just looks like a cloud of points. And those are all those different slopes. Okay, so this raises an issue. Yes?
Sorry. How are you getting variance of SI squared? I thought it was fixed in your case, wasn't it? Like, what is variance of SI squared?
Variance of SI squared as a sequent, as the empirical variance of the set of numbers SI squared.
Spread.
Oh, so SI squared is not variance of the third singular value. You don't mean that?
No, it's variance of the set of singular values,
got it.
which is just a fixed set of numbers. And so one issue that comes up. So I said this is pretty much unbiased, but of course it's not unbiased if you're truncating it at 0, because you get. You can have big spreads, and the spreads can cover negative values. And so if you say heritability has to be positive, then you have to truncate it at 0, either truncate or simply throw away the negative estimates. In any case, the positive estimates you end up with are going to be biased and have an upward bias. And so I got interested in the question of, well, what do people do with it, with negative heritability estimates? So in the original, and it turns out it's a complicated story. In the original description of the model, h squared was the ratio of two variances, so it had to be positive. But to misquote Tolger from before, a model is not a statistical model. So these variances are not in the statistical model. And so the statistical model that we have, which is this multivariate normal model, does not require, there's no natural sense in which phi greater than 0 is a natural constraint for that model. So you can say for physical reasons, and this is where, so I got to this at some point, and I was just discussing this with Andy, and saying, well, one could say for physical reasons, phi, the thing we're modeling, phi has to be positive, heritability has to be positive, and thus we want to impose that constraint. We're taking this subset of the model. That's something you do. But that raises the question, well, is it true as a physical matter that heritabilities have to be positive? Right? And so that depends a bit on how you define heritability. So in this model, right, h squared is a regression coefficient. It represents a correlation, not a variance. So certainly as a statement about the data, there's no reason why it can't be negative. And you can think of it as, and this is the way I originally thought of it, is something like the correlation between differences in phenotype and differences in genotype. So negative heritability would mean subjects with more similar genotypes tend to have less similar phenotypes. Well, is that possible? And, well, here's a theoretical model to explain why it's possible. So it can arise from gene-environment interactions. I'm not assuming any gene-environment linkage. So if I have P loci with a linear reaction norm with respect to the environment, which I call omega, that's to say, okay, wait, really?
My regression model.
Variance is negative.
I started 20 minutes ago. Okay. So we're saying that people that in different environments, I'll just say that the gene has, if you have the one, there are types 0 and 1. If you have the 0 type, then that doesn't affect your character. If you have the 1 type, then in some environments you have a positive character, and some you have negative contribution to the character. Okay, so the result of that, so I'll just show here the outcome. If you have 2 random individuals who agree at k sites, then we can compute the expected squared difference, how much you expect them to vary in their character. And that comes out if the effective alleles are more common, this will increase with k. So the more alleles you have in common, that makes sense, right? The more alleles you have in common, you might have come from similar environments, you might have come from different environments, but that will, if you come from different environments and you have a lot of effective alleles, then you're going to have different characters. So the overall effect is to make them more dissimilar if they have similar genotypes. Negative estimates of heritability have sometimes been reported. Here's an example, but here's what they say about it, which is essentially that they use, for convenience, to maintain unbiasedness, they will maintain the negative estimates, but only to average them with other ones. So they don't believe in them, but they see them as statistical necessity. Here's a paper that actually Jonathan Marchini pointed out to me from J.B.S. Haldane. He says that the definition of heritability is due to Lush and is defined as the coefficient of regression of the mean value of a given character of 2 sets of relatives. So Lush in 1936 said it is the portion of variance which is due to the additive of genes in this population. But later he said it is the fraction of the observed or phenotypic variance caused by the differences in genotypes. But in the same paper he also says it concerns differences between individuals when the importance of variance causes to be assessed and expressed in terms of their squares, in terms of variance. But it may be convenient to use correlation and regression. In any case, well, I won't go into Haldane's analysis, but anyway, it involves the fact that it involves a maternal interaction. So if your mother had this condition, you can't have it, but it's a genetically determined condition. Okay, so let me say a bit about the spectra, which is that so they tend to be, so if the entries are independent random entries, then we have theorems which say that we'll have a particular form, which is this, and it fits extremely well even for relatively small matrices. Here are the eigenvalues for singular values for the data from the Northern Finland birth cohort data. And here's the corresponding Marchenko-Pasteur distribution. Now, even a mathematician like me can tell that that's a bad fit. But of course, this is right. So the problem is that these are not independent entries, and so the effective number of SNPs is actually much smaller, right? Because of linkage disequilibrium. You can get a significantly better fit if you take a smaller value of p, which seems like it more or less corresponds to the amount of independent information in the SNPs, although we still need to analyze to understand better these relationships. Here's a log-log plot of this theoretical distribution against the NFBC eigenvalues. Here are a bunch of different eigenvalues for different genotypes, and you see they can look quite different. Oh, this is the genetic relatedness matrix. So these are the yeah.
Z transpose.
Yep. Okay, so dependence between individuals creates small singular values, which is good for the model, but bad because it probably isn't coming from what you want it to come from. Dependence between SNPs reflects linkage disequilibrium, and this essentially means that is what explains this saturation effect, which kind of naturally occurs in this model. And population stratification reflecting a complex dependence across individuals and SNPs. The singular vectors will, in great generality, have a particular distribution, which is essentially to say that they're like independent normals, except that they're normalized. They have to be orthogonal to each other. But this determines what comes later. I won't say anything here about measurement error, except that basically measurement error isn't a problem for the model, regardless of whether it comes from SNP measurement error or phenotype measurement error. So in my last few minutes, I want to talk about actually something which relates to what Sid was saying at the end. What happens when the genetic effect really comes from a small set of sites in linkage disequilibrium with the observed SNPs? And I'm going to actually analyze a slightly simpler question, which is really kind of the same. What happens when genetic effect comes from a small subset of the observed SNPs? So essentially, this is the same question. As long as you could predict the unobserved, the causal SNPs from some subset of your sample, to the extent that you can't predict it because there isn't enough linkage disequilibrium, then you'll underestimate heritability effects. Okay, this is something which, of course, is talked about in the literature if you don't have enough coverage. But assuming you have enough coverage, you're in more or less the same situation if you have a subset of SNPs within your sample, or if they just fall between your sample but are linked to them. So let's assume that there's a subset of K SNPs that have IID normal effects, and we condition on the sum of squares being a particular number, sigma g squared, which we think of as the genetic variance, the contribution of genetic effects. And so I'll call it the random causal SNP model, where eta is a uniform random set of SNPs. I won't necessarily assume that, but I can draw further conclusions if I do assume that. Otherwise, there's just some unknown eta, some subset of SNPs that are effective. And then I have the phenotypes are simply produced just as before, but just by summing over the causal SNPs, and the others have effect 0. Now, then we get the data, and we estimate the parameters using the standard random effects Gcta model. So we don't know what eta is. We don't know what k is. We just got these data. We think that all the SNPs are effective, and so we fit the Gcta model. Okay, so there's general theory that tells us that the MLE will converge not to the true phi, because true phi isn't really reflected in this model. But it will converge to biased estimates, which define the closest fit among the models with p-causal SNPs. Right? We're fitting a model with p-causal SNPs, and there will be some parameter that we'll end up with, and for large, as samples get large, we'll be converging to that number, but it won't be the true phi, but rather it will be this phi star, which is the closest one to, right? So we have two different models. We have a k-SNP model and a p-SNP model, and those are just statistically different models. And among the k-SNP models, the p-SNP models will be one that's closest to the true model that's really generating the data. Okay, and then we'll have some parameter which I call phi star, and we can solve for this. Now, in principle, we could get an arbitrary bias, and this reflects the fact that our k-SNPs causal SNPs could be in some arbitrary set of linkages. They could happen to be linked to everything else, and so you'll overestimate your effects. Okay, or they could be linked to nothing else, in which case we'll underestimate the effects. Okay? So there could be an arbitrary bias, but if we think that these causal SNPs are just a random subset of all the SNPs, which is a standard kind of assumption to make, they don't have any special properties, then we can actually compute the distribution of the phi star and h star squared, and what we come up with is that the difference, right, so h star squared is something different from h squared, the true heritability, and it has mean zero, averaged over all possible choice of causal SNPs. That's the overall, I mean, for the matrix you've got, it's a biased estimate. Each set of causal SNPs will produce a biased estimate, but if you average over all the different ways you could choose the causal SNPs, the bias averages out to zero, which is good. And the variance is given by this formula, which differs from differs from our original formula for variance of the estimates by this factor. So essentially, the variance, if we kind of treat this as a combined problem, right? How much uncertainty do we have in estimating h squared? It turns out it's increased by this factor, which is actually going to be pretty small in general if k isn't a tiny number. So here's a simulation with p equals 5,000 and n equals 1,000 and n equals 2,000. So the curves are the theoretical prediction, and these dots are showing basically the variance of estimates over many different choices of the causal SNPs. Okay, so these theoretically they should lie right on the curves, and they come pretty close. Here are a bunch of simulations derived from the NFBC.
Sorry, what was your number of SNPs in your simulations again? Could you just go back to that?
5,000. So that was for numerical reasons. But these are simulations that were actually done with the whole NFBC data set, and basically just randomly picking 10 or 30 or whatever of them to be the causal SNPs, generating random phenotypes. And here you see how, right, if you happen to get one of the matrices, one of the setups down there, you could, and there's nothing you can do by taking a bigger sample. Those are simply the causal SNPs. And however big your sample is, you're still going to get that error. But averaged overall, the errors are zero, and the variance in the error is small. Okay, so sorry I went a bit over, despite your attempting to stop me. But anyway, the summary is that a simple random effects model gives reasonably unbiased estimates of heritability. There can be considerable bias if we truncate at zero. Truncation bias and variance can be large for a large number of independent SNPs, but fortunately there aren't all that many independent SNPs in the human genome. And the fixed effects model behaves reasonably well with regard to some simple sorts of models misspecification. So that's it.
Questions?
I think I'll go later. So
I did want to, when you were talking about negative heritability.
Yes.
So there's also a literature in, mostly in evolutionary biology, where they attempt to estimate what they call the genotypic variance-covariance matrix, which should be, positive definite matrix, or negative definite or something. It should have some appropriate sign structure. It's a variance-covariance matrix. But when they do the estimates, they often get matrices which don't obey that sign structure. So it's an analogous situation, and there's actually a number of papers where they talk about, why do estimation procedures lead you to G matrices that we shouldn't be getting? And it's a multivariate. It shows up in a multivariate generalization of the heritability.
I see.
So this was somewhat related to what I spoke about, but I just want to ask you, in your opinion, as the model as you've structured it, what does it give you? Does it give you the heritability conditional on the genotype matrix? Does it have a physical meaning? What do you think of the number you calculated?
Given the model as it's formulated here, it's not. It doesn't matter what the genotype matrix is, because the genotype matrix is only being used to multiply by these U's. And the point is, it's giving you what the calculations are telling you is that it's telling you what the variance is of this vector U.
But the question is, do you feel that are you keeping track of the people in Snips? Because is this a global parameter? Like, can I tell a person the estimate is so and so and standard error is so and so, or is that not a reasonable statement without specifying Z? Because you are conditioning on Z, you have to know Z at all times.
Well, yes. I mean, so there's something, as I was saying before, there's something weird about the normalization, and the normalization does depend on which people you happen to get. And if you normalize differently, you would get a different variance, because what the normalization is doing is reweighting the contributions of different SNPs in the total variance calculation. So that's the point. But you would certainly expect. Well, I don't know. I mean, if you believed that the frequency of a gene, the frequency of a SNP, or the minor allele frequency, is independent of its contribution to the phenotype, then that should all kind of average out. But I can't say whether that's a good assumption.
Okay, sorry, I wasn't phrasing my question correctly. What is the biological interpretation of that number?
Well, the biological interpretation I take to be that why are we formulating an additive model here? In a pseudo biological interpretation would be that having one or the other SNP contributes a certain amount to the character, and that number of contribution is summarized as this U corresponding to it, and then what H squared is telling us is what's the sum of the U squareds.
This was one of the questions I struggled with, and this was, how do I attribute a meaning to this number? Because it's not, I didn't find it very straightforward, at least. When you think about, because the conditioning on Z, like you do it, And I was like, well, if your conditioning one said, is it saying you have the same set of people, the same set of SNPs, and you keep repeating the experiment with a population which looks just like that with that snapshot?
I don't think it matters because
Okay.
I mean because in some sense, you're multiplying it by some matrix and getting some numbers out, and if the only problem that would come up would be if you had chose your matrix such that, for instance, they were all parallel. They all had the same genotype or something, which would be reflected in having an extremely skewed singular value decomposition, and most of the singular values being 0. In which case, you're the same problem as in a linear regression, where you've done all your measurements at one point. But otherwise, you have a spread of singular values. It's just not going to be. It doesn't matter what they are exactly.
One of the themes, many themes here. One is a very old problem, just like missing heritability, mortality, things that people have been thinking about for a long time. I'll say this is data and work that's very early, something I've been thinking about for a while, the methods I've been using for quite a while. But in terms of this particular application, it's sort of a newer idea that I'm starting to work on with Tulja and Ben, so very interested to get people's thoughts generally and in particular on this application. So again, we have Haldane again here and thinking about the interaction of nature and nurture. Before we had much genetic SNP data around, obviously a lot of theoretical work on it, a lot of interest for a variety of reasons in terms of thinking, especially for social scientists, going beyond and sort of in some ways as a criticism of saying everything's genetic, but say, what does the environment bring to things? And then also on the environmental side, as a social scientist thinking, when I'm looking at particular social exposures, would my effect estimates or association estimates, could they be refined if I'm taking into account some genetic information? So he goes through a number of examples in this paper in sort of a simplified case of 2 by 2. So that was about 70 years ago. About 25 years ago, Ruth Ottman at Columbia, many examples of this, but had kind of a nice overview of some of the different ways we can think about genes and environment. Here she talks in the medical sense, risk factors and genotypes being involved in disease. The A and E here, not what we typically think of, not really G by E. This is something where a genotype affects a risk factor impacting disease. In this case, they just both have independent effects on disease. And these are both kind of the primary paradigms that's driving most of the way people are thinking about things. And then she delineates 3 different sort of examples here. One which is a little more of the sort of classic G by E in a way, where you have a genotype and risk factor when they would only matter when they're in combination with each other. Today in my examples, I'll be thinking more about these B and C, where you have a risk factor that then the factor association with a disease is modified by genotype, or in the case you have a genotype to disease where that's modified by a particular risk factor. So this is something that doesn't need to be hammered home too much, but just the problems with G by E and replication of G by E. A nice example here of the literature. 96% of the first reporting of G by E studies were significant, and around 27% of replication papers were able to replicate those findings. And this, I believe, is of published data, and so this isn't horrible, but obviously the biggest concern about G by E, especially sort of the candidate approaches out there in the literature, what's the sort of publication bias, what's the sort of transparency in terms of the type of G by E that are being detected. So on the one side of things, there were things that proceeded in sort of a candidate fashion, where we're not sure about publication bias. And then probably in the last 10 years or so, there's been a lot more of sort of statistical learning or machine learning approaches to looking at epistasis and gene-environment interaction. And so a lot of this work has been done by Jason Moore at Vanderbilt, but a lot of other people, and literally dozens of different algorithms that are out there in the literature for people sort of scanning through in an agnostic way to look at how clusters of genes are related to particular phenotypes of interest, and to a lesser extent some of those approaches for G by E, which I think it is sort of a type of approach that I'm very interested in. So in terms of goals and thinking about how to look for G by E, I'm interested in the strengths of both of these approaches. There's a lot of questions where we have pretty good priors. We have, for example, here I'm going to talk about the priors of the polygenic scores, the priors of what we know in the environment that are related to a particular disease. Here I'm going to be talking about heart disease in HRS. So, a lot of work, a lot of literature on what we know about those risk factors. But the question is, when we looked at some of these primary factors with each other, we don't see necessarily the importance of G by E. So in thinking about some approach for looking at G by E, there's a few criteria that I was thinking about that would be ideal. The first, kind of dealing with this publication bias issue, is that the approach would be transparent, repeatable. Another, the number one thing, obviously, in G by E is talking about sample size. If we're thinking we need, at least 100,000 for sort of just looking at genetic effects, that essentially becomes amplified. In David Hunter's sort of big review in 5 or 6 years ago on G by E, he had some sort of sample size calculations that showed for the sort of effect size we would like to see. We need really, really pretty large sample size. And then, but the issue comes up about when we care about high quality environmental measures, and we really need those high quality environmental measures, how much are we really going to be able to meta-analyze studies to really look at G by E? I think it's changing with some of the really large cohorts that are out there. But ideally, I would like to be able to look at some of this stuff in sort of a relatively small sort of data set like HRS. Robust, obviously the replication has been a big issue. We want something that is not spurious. Multidimensional interaction is kind of another thing on the wish list. It's not clear to me that most of these should be just operating as two terms. So it may be more than just one genetic factor or one environmental factor, or just one genetic factor and two environmental factors. But it may be a number of things that come together, and within those subgroups where you see real heterogeneity in either an environmental association with a phenotype or a genetic association with a phenotype. And then the fifth is interpretable interactions, and that's kind of one of the issues with a lot of the really robust machine learning or statistical learning methods. Because of all the resampling that they do, or because of the particular type of approaches, all you can really say is, the outputs that you get from these type of models are that, well, these factors are more important than other factors, but you're not really able to test something specifically with your priors, and you're not able to see so clearly, what groups may be most important for predicting your outcome. So random forest, is one of the sort of classic examples of that. So the approach that I'm going to take here is this model-based recursive partitioning, which is a particular method based on recursive partitioning or decision tree analysis, which has been out in the literature for a really, really long time. So it's a fairly, in terms of algorithms, it's a fairly basic, well-known sort of algorithm that's been out there. But these folks did a little bit of an adaptation of that, in that they allow you to fit, and again, when I say model here, I'm not talking about a told you model, theoretical model, but a statistical model, where they allow you to fit a structured part of the model where you have priors about the factor you want to investigate and force that to be in the model. And then essentially search over a number of covariates and say, for this statistical relationship between an outcome and my exposure, is there heterogeneity in that relationship? So it's not about just predicting your outcome based on a number of factors, which is sort of 95% of the algorithms that are out there, but actually looking at that association. And does that association vary? Is there heterogeneity over subgroups from any of these other factors. So one way they describe it is, they talk about, they frame it here in terms of Occam razor. Does the model fail to describe the whole sample? You have a relationship that you think is there based on your priors and your structured statistical model. Is that stable, or are there some subgroups over which that relationship is not stable? And essentially then that can be used to think about a gene-environment interaction where you would have a particular gene, a particular outcome, and say, is that stable over a number of potential environments? So this has been implemented in an R package. As I mentioned before, it fit the structural part of the model, and then scan over remaining covariates to see if there's different effects by subgroup, or different associations, I can say. So just as an example of the code, it's very simple. What you do is you have your dependent variable here. You have your structural part of the model here that you force to be in the model. And in this case, for this example, all I'm forcing to be in the model is the polygenic score for cardiovascular disease. And then we can have, say, a number of other covariates that we search over. And there's a number of then tuning parameters you can do for the model. So we did this. So I haven't, to my knowledge, seen this used for genetic information, genetic data before. We have a paper that was out earlier this year using it on observational data, where we analyzed whether there's heterogeneity in the effects of an intervention, a social intervention, on particular outcomes among kids. So this was an evaluation of the moving to opportunity housing randomized housing voucher intervention, and it's well known that there's a number of for some outcomes it applies to girls and not boys. It's very site dependent, and so we wanted to look more broadly across a number of factors and say when you have this intervention of this housing voucher, what factors does it depend on? What are in epidemiology we call it effect modifiers. You could call it heterogeneity. And so this is just sort of an example of the output you get from the model. And so it essentially does a decision tree. And the way it works is the algorithm just looks through all the covariates that you specify based on your priors and says at any cut points for any of these characteristics, do we see heterogeneity in the association between, in this case, the housing intervention and psychological distress for adolescents. And so the first split point is Chicago, then it repeats it through the data, and you can have another split point, and you get down to these nodes that then are testing based on p-values for these splits. So you have these nodes, which are essentially groups of characteristics. So this node here is just everyone who is at the Chicago site. This node here then is people who are not at the Chicago site and who are male, etc. And then you can calculate what the effect sizes are in each of these different groups. So any questions just basically about, go ahead.
What was so special about Chicago?
That's a good question. It's come up before. I'm not an expert on MTO. There's a lot of different, but it's very consistent. But it's not just with this trial. I mean, if you look at data from any sort of trial with there's been 4 or 5 different sort of studies I've worked on that have 3 or 4 sites, and you'll see one of the sites, that things don't work there or look really different. So it's pretty common. And, it could be something about the context. It could be something about the way the vouchers were implemented there in particular. But
it's not always Chicago.
Yeah, no. I think there's 5. There was L.A. I mean, other people know more about this than I do, but there were a number of sites. But yeah, it's not just something about Chicago. And it was sort of null in Chicago. But there's some subgroups where it's actually worse for distress and some better for distress. So overall, Chicago, at least it didn't harm people there, right? And it's more for the boys. It'll be, it could be doing. So just quickly, I used the health and retirement study data. I didn't do any weighting for mortality selection. So everything, a big caveat here. But we'll maybe get to that with the next version. So I'm using it's the longitudinal data for 92 at baseline. The dependent variable I'm just using here is prevalent heart disease in 2008. There's a lot more things we can do with sort of incidence and longitudinal. For now, it's just prevalence of heart disease in 2008. The polygenic score is a genome-wide score from the cardio meta-analysis. And then I also did sort of, you'll see later on, a top hits analysis where I was trying to look at potential genetic modifiers. And these are from a recent meta-analysis of cardiovascular disease, so about 20 of the sort of top hit Snips. For this sort of first pass, I have a pretty limited number of environmental and classical risk factors data. The method, there's no problem with going up to a couple hundred covariates if I wanted to. But I picked kind of the main sort of social environmental factors that have been associated with heart disease, and then as well as sort of the classical risk factors for cardiovascular disease. There isn't too much missing data on any of these variables, but I did do a missing imputation with using a random forest imputation approach. What I did, so one of the big problems and challenges with the regression trees is, and really any of these type of methods, is overfitting your data. If you have enough parameters in there, you can fit your data really, really well, but that's not going to be very stable, and it's not going to do anything outside of your sample. And so that's really the big elephant in the room with any of these approaches. So with decision trees, for example, that's sort of how Breiman came up with random forest, that it was selecting on subsamples of your data and repeating it in order to get a variable importance and have more stable results. So like in our AJPH paper, what we did for these trees is we created multiple trees on subsamples of the data and only interpreted the split points that came up on a large number of trees. The approach I'm going to take here, and this is something, a longer conversation that we can have about what the best approach is. What I did here is I split the HRS data in half randomly. I just did a random generator, and this is all in non-Hispanic whites, I should say. So there were around 9,700 total, or 9,400. And so I completely split my sample in half randomly. So I created the conditional regression trees on half the sample, and I created these nodes and subgroups for the interactions, and then I tested on my, so it was a training sample, and then my test sample, I said, does this really hold up? Are they different on this completely separate data? Okay, so here's just showing you that the polygenic score is nicely distributed here. And this is just a correlation, just as a little bit of background, just a correlation matrix with a really dark blue being a strong correlation. And this is just to say, for most of the variables that I'm using here on the diagonal, they're correlated with each other. They're not that strongly correlated. Anytime you're doing this kind of thing, you kind of want to, if there's things that are correlated above like 0.5 or 0.6, the algorithm's gonna wonder which to split on, and you can get kind of arbitrary sort of split points if the data are too similar. But I'll just point out too here that the cardio score is here, and actually, if you look at that correlation of the cardio score with any of these other variables that I had in here, we don't see the sort of gene environment correlation here very strongly with our data. Some things are obviously like systolic and diastolic are pretty strong correlated, weight and waist, but other than that, not real strong correlation. This is just as a preliminary showing the dependent variable here is heart disease risk, again in 2008, and looking at the association. I did a GAM model just in case there was a nonlinear relationship. It's actually a very nicely linear model, so everything else from here on out is kind of assuming a linear model. And it actually explains around 5% of the variance. And this is just a z-score of the genetic risk score, and showing, at higher levels of that risk, there's an increased risk of heart disease. And as the so I pick that as kind of my primary sort of genetic factor. And then for my primary social factor, parental education. So the sort of parallel there being like both are sort of inherited by an individual at birth, your social inheritance and your genetic inheritance. And there we see by years of education, lower rates of heart disease, and actually it's kind of interesting. A 5% variance explained, and the association was very, very similar. So this sort of parental education endowment, this genetic endowment, almost equally strongly associated with cardiovascular disease. Just to kind of talk about any of these factors that I'm going to be scanning over, again, the dependent variable here from these three models is heart disease. And when I include a bunch more of these factors in the model, which you would kind of expect from that covariance matrix, the association of the polygenic score doesn't really change. Same with parental education. They're not really predicting through any of these other risk factors to the most extent, for the most part. Okay, so let's get on to the first regression tree that I do. So this is predicting heart disease, looking at the relationship between the polygenic score for heart disease and heart disease as the dependent variable, and examining whether that relationship between those two variables varies depending on any groups that I could create based on this algorithm. And so the first split point here is age, and the way you can read this is sort of you're splitting off to this point, so a p-value for the split. You're splitting if people are older than 67, they go on this node, less than 67, then it repeats with each of these nodes. So the variables that come up here were wealth, age, earnings, and age continues to split, obviously, as we would expect. So what's shown at the bottom here is the relationship between, similar to those plots I showed earlier. On the vertical axis is heart disease, either a 1 or a 0, no heart disease, and then this is the axis of the genetic risk score. So this kind of shows across these subgroups how much variability there is in the association between that polygenic score for heart disease and heart disease. So for example, just to take the strongest example here, if we take this node here, there's a very strong relationship where there's higher levels of, you're at a higher level of heart disease risk at higher levels of that score. Whereas some of these others are either flat or going, actually even going down a little bit, sort of the opposite sort of association. I'll say another thing I did, so there's a lot of tuning parameters you can do with these trees to, if you want to grow them sort of and get to really small groups or be much more conservative about the number of splits you're going to have. I set it so that the minimum node size would be 5% of the population. So my prior here is, that's going to just be more stable, and I'm actually not really that interested in identifying, subgroups of 10 individuals who are at some. First, I don't think I can, but also it's just sort of from a population health perspective of less interest to me. So then what I did is I took these nodes, and just for an example, I took sort of the two strongest positive associations and two strongest negative associations and said, now let's try those. So now let's split the sample. Let's not do anything like this anymore. Let's just split the sample into those subgroups. And then let's apply this to the test data and see if we see these associations hold up. So these are just the definitions of the nodes here. This was the overall association. These are the point estimates and the confidence intervals. And so what we see is that they're not, dramatically different here from that overall estimate. So if you had a confidence interval on that estimate, these groups wouldn't be, drastically different from that overall population association. But we do differentiate these subgroups that are different from each other, which is really what the algorithm's testing. Not are they different from that overall relationship, but can we identify subgroups where that association is different from each other. So in this case, when I do it, there's a bit of an overlap here, but at least for the sort of the two strongest on either end, I am able to identify these, these associations that differ. So I repeated this again now.
Can you go back to the slide very quickly?
Yep.
I mean, so it just strikes me as curious that between 17 and 18, the difference is basically just, so 18 is those over 80, 17 is those between essentially 70 and 80.
Yeah,
right?
yeah, they're from that they're from these two differences here. And so this is around 200 people. It was only based on this slight age difference.
Okay.
And then it replicates,
Yeah.
So, and we'll get to these examples at the end. I don't see a clear pattern here in terms of, in all cases when, at people in sort of worse socioeconomic environments, the relationships tend to be weaker or stronger. It does seem idiosyncratic, which is usually, just noise, right, when you see things that are... But on the other hand, these may be things that there is something there, and it did give me confidence when I saw them, replicated in that sort of test sample. But yeah, it's just based on some of those age differences there.
I've forgotten
Yeah.
What is it that you're predicting?
So predicting heart disease with the polygenic score, for the genome-wide polygenic score. And that's what's the really different thing about this. It's how that relationship differs. It's not just predicting heart disease. It's how that relationship differs.
The next slide was an out of.
Yeah, and the next one is out of sample. Exactly.
What we see is that in some age group, heart disease is positively associated with the polygenic score, and in other age groups, it's negatively associated.
I mean,
yeah.
Like, I don't want to make too big a point of it, but
Yeah.
what you were showing is that for those basically 80 and older in that sample, there was, genetics don't matter. I mean, which is...
Yeah. There you go.
consistent with the idea.
It does make sense. Yeah. No, absolutely. Right. Let's see. Is that, so in 16, yeah, that's 79, that node 18 is the 8-year-olds. Yeah. Yeah. All right.
I feel like I should leave now.
Yeah.
Your job is done.
So I did this. I don't quite like this approach as much. I like sort of kind of clear temporality here, but I was just interested in if you're including the risk factors that HRS has measured in 06 or 08, do those interact with any of the environmental factors or the genetic factor? They tend to overwhelm things a little more, and you don't see I think you see, you don't see in this particular one then the wealth or earnings coming in anymore, but you see things modified by cholesterol. Oh, occupation came in, that's right. So occupation was in there, but gender and smoking and cholesterol, which then modify. And so I did the same thing. I won't talk through all this here, but I did the same thing. In this case, then 3 out of the 4. So this node 19 wasn't really replicated in the training sample. This was pretty much spot on, in the test sample, spot on with that overall estimate. But the others tended to be showing that similar differentiation that I saw in my training sample. And just to contrast, so that this is doing a standard regression tree approach where you're just predicting the outcome. And in this case, none of the environmental factors were coming in. And that's sort of the motivation, and actually the the polygenic score wasn't coming in. So what I'm doing here is just saying, throw all these things in the model, what predicts heart disease, which is more of sort of a typical way of doing these sort of algorithms. And in this case, the polygenic score doesn't come in, none of the environmental factors come in. It's sort of age and proximal risk factors here. And this was sort of the reason that, the thing that motivated me to take this approach, that I could actually test some of the theories and test things I want to test. This was the same case with MTO. If you look at what predicts adolescent distress in the Moving to Opportunity study, the intervention, is not on the top list of the 20 things that predict adolescent distress. There's a lot of other things that predict it. It doesn't mean we're not interested in it, but it's not one of the primary predictors as you would actually expect. And so here's then doing a random forest, which is a little more robust. And if we're predicting then heart disease here, obviously age, cholesterol is very high. Getting down to sort of the polygenic score is down about here. Parental education's a little higher. But wealth is down here. So these aren't sort of the strongest sort of overall predictors necessarily. So then what I did is also interested in sort of flipping this around and looking at the other side. Now, instead of polygenic score, I fix in the model parental education. So I say between parental education and heart disease, are there any of these top hit SNPs that modify that association? So then this is looking at sort of the other Ottman construct of when you have an environmental factor, are there any of these 20 SNPs on their own that change how that's associated? So the algorithm, these were barely at p.05, did pick up a couple of SNPs that had some modification of that overall relationship of this. So this is years of education here, heart disease. But as you can see from these, they're relatively similar. There's not a major difference in that association based on any of these SNPs, which kind of makes sense. I mean, each of these SNPs on their own, don't have a strong overall association. The other thing, of course, is that the big sort of background here with both the polygenic score and the top hit SNPs is that they're coming from the GWAS that are averaged over a lot of environments. So it's one of the kind of big assumptions with this particular approach here that I'm taking that information from the priors of the GWAS.
David, before you move on with the SNPs, are these? Does the model know which is the heart disease associated allele?
So I'm only feeding it 20
the counts of disease associated alleles.
Yeah.
So essentially what this is sort of a competing risk story where carrying elevated genetic risk for heart disease diminishes the risk increment associated with the socioeconomic disadvantage.
Well, it doesn't make much of a difference, right?
These aren't differences from the mean. These are just the actual slopes.
These are the actual slopes. These are the actual slopes of that relationship, and so it doesn't really differentiate it. And then this was just doing the same thing, just to be in parallel, where I also added in those cardiovascular biological risk factors, and none of the SNPs sort of came up there as well. Okay, and then just with the test replication of that one from before, we don't see these as being very different based on the SNPs. Okay, so the substantive sort of summary here, we'll add Ben's bullet point, but in 3 out of 4 cases, there was sort of a better, in those particular nodes, there was a better social and economic environment was associated with lower polygenic score associations with heart disease. The genetic risks seem to be strongest between around 68 and 80. Obviously there's this selection that's happening, but then you have when heart disease is happening as well. You're not going to be picking it up so much in the younger ages where there just isn't any heart disease. In terms of gender, there wasn't sort of a clear pattern of some, in all cases, male was associated with weaker or stronger. It sort of was split, but it wasn't an important factor throughout for sort of differentiating some of these. Cholesterol, interesting here, there was consistent cholesterol was coming into the model a lot. Having bad cholesterol was associated with a weaker genetic risk, maybe sort of outcompeting that essentially, and then smoking was sort of split on that. So I do want to come back and just kind of be responsible and come back to the question of the robustness of this, how replicatable this may be, and to say that there's been some great recommendations. This is one example in the literature of how you should approach sort of G by E, and a lot of this approach sort of ignores. They talk a lot about having very strong priors for these particular tests. Which I'm fully in agreement with. So none of what I'm saying here is against sort of having strong priors and testing particular genes or taking that full genome approach. It's just instead the idea of thinking about if there's sort of a middle pathway between the complete search and between the theoretical-based model for discovery. And I see this. Even though I was doing the training thing, I see it very much about discovery and sort of description rather than anything causal here. But as a way to sort of find new potential things in the literature that we may not have known before because of sort of the limitations of our prior data. And so this is sort of the balance that we were potentially trying to achieve. I do think it was kind of interesting I was a bit skeptical whether I would find any sort of modifiers of the polygenic score. I kind of had this prior that, well, because you're adding up so many alleles, that any of these sort of interactions would be, based on particular SNPs, and you'd essentially be washing anything out. So it was interesting to me that at least from this data, I didn't find that to be the case, and that actually, I was able to find some of these interesting modifiers of this sort of overall genetic risk, not just sort of particular pathways of genetic risk. And again, I think that the training of test samples one of approach. You could also do this based on, as we did before, multiple sort of subsamples of the data. And thanks.
So,
yeah.
Questions?
I don't understand terribly well what you've done, although it looks very interesting, and I want to.
Yeah.
So suppose that the true underlying reality is that polygenic risk is multiplicative with with age, cardiovascular heart, a sort of underlying cardiovascular risk by age, which I imagine is rising in a sort of Gompertzian way, so that it's maybe twice as high every 7 years or something like that. And then I'm not sure when you do the tree analysis, is it essentially fitting an additive model so that if it says, oh, the risk is higher for people in their 70s than it is for people in their 60s, and it treats that as two nodes, could that just be because the true model is multiplicative and this is a sort of additive structure that's being searched for?
Yeah, absolutely. I mean, I think you would pick that up. I mean, this is sort of capturing the multiplicative interactions, and I think it would pick up any of that if you just have this increased, especially just because of your power to pick it up. But because that relationship, I mean, it's really pretty agnostic to if there's anything that's causing that relationship in your model for that genetic risk score to the heart disease to change. It's going to pick that up as a group. I will say that I only fit the polygenic score and the structural part of the model, but if we wanted to look, say, everything else other than age, you can also put age in that sort of structural part of the model, controlling for it just as you would, in a typical regression, and then search over everything else, which I think is
sex, or I don't know.
Yeah, exactly, which is one of the things I really like about this model, because I mean, obviously age and gender are so powerful that any sort of little correlation with anything else, it can just be kind of overwhelmed. So I think that is, it's a very good suggestion to structure that and then search and see if there's anything else. Yeah.
So, well, I was saying, I thought it was really good that you did these out of sample tests. And one thing that I guess I'm always suspicious of with these kinds of models is that you're, in principle, you're searching over a huge space of potential models. And it's not, and so I don't know, I was wondering if you know something about how well you can control for the kind of, the potential, exponentially many multiple comparisons you made. I mean, in principle, if you give yourself enough freedom to search out subgroups, you can find any relationship you want.
Yeah. No, and that's been all. I mean, that's the last sort of 10, 20 years in the field is all sort of dealing with that problem. And with these trees, it's sort of like, they call how big they're grown and then how they're pruned back and resampling. So it's the sort of fundamental issue about it. It's sort of, so you can't ever do this without doing a test and a training sample. I think the way I've dealt with it is by being pretty conservative, that I'm not going to allow it to create a group unless there's a lot of people in that group, which to me seems, it should be more stable. But you're still searching over all of those factors. So, I mean, the other thing that I didn't really show here is, repeating it as well, and also you get output on sort of what the next best split is. That's the major issue with that, right? You have some that's like points. It's the same thing as like with how horrible a backward and forward selection model is. And so that's where the fitting it on subsamples of the data is really nice. But you can really go back and look at, what's the second best split. And so when you do these trees and say, let's refit this with the second best split, refit it with the third best split, so you're not being sensitive to some particular split that's a little bit better. And in that AJPH paper that I showed, we had these trees and, getting all these little factors that we thought were really interesting. We fitted on 10 subsamples of the data. And, our initial interpretation, if we were completely naive, would have been there's about like 15 nodes that are very interesting. When we look over 10 trees and say it needs to be in at least 8, there's around 7 nodes, that are interesting. So doing that definitely does cut it back, which is what you want. So it's
so
not a finished story.
Sorry.
Yeah.
I was just going to answer part of his question, so I'll wait up.
No, Emma? All right, you go ahead.
So it's a greedy forward stage-wise approach. So you're greedily just picking the variable you want to split on. So there's no guarantee in these things in any case. They're an approximate solution. You just hope that, if your answer is this, you get within some percentage of it. So
well, no, I mean, the problem is just that if you allow yourself enough flexibility in how to make the split, then you can be, you could just be picking out the 500 individuals, right? If you allowed yourself to just pick individuals that create the biggest slope, you can create an arbitrarily big slope.
Yeah, oh, absolutely.
So that's the point. It's not just a question of how do you choose among the options that are available. It's how many options you give yourself for choosing.
But he's regulating that by fixing the minimum number you allow in a bin. All right. Yeah. Sorry.
No, but
Olga doesn't seem to be here, but I wonder if we should go on to general discussion in which some of these points I think will continue fairly naturally. We've had two very different pieces of this meeting so far. In the morning, we heard in some depth work that is garnering a lot of attention, that is in the news, that is drawing on very large enterprises and the polygenic scores that have been created from the big consortia, although now being used in individual research in creative ways and in the Oxford Consortium, and Kathy introduced us again to a very large enterprise, and we're hearing richly about how much is being gained in work that we've all been hearing about and eager to hear more about over quite a while. These are sort of introduction to things that are out there and happening. This afternoon, we've shifted gear, and a lot of what we're hearing now is new to this meeting. That's the first time it's being presented, or the first time it's being presented with the audience of people who are debating. The technical things may sound like they're appealing to a narrower group of technical people here, but this is the meeting where they're first coming up, and this is the first time in which most of the players from across the ocean and around the country are here to discuss these things. So this is both morning and afternoon worlds are cutting-edge research, but different things are happening in the afternoon because we are, in the afternoon, taking up issues that are perhaps first now being talked about in depth around the world. Now, what's the importance of this kind of afternoon discussion. So I'm reading afternoon discussion. I doubt that any of it will be of the substantive importance of what we've been hearing from Melinda and from Dan and others, which are capturing the imagination of a very large part of the social science world. But these issues that may look small and technical have far reach. So what is being argued about down the road, I think, is going to affect the direction that this whole field goes. In particular, in genome-wide studies, there are three games people play today. There's GWAS, there's Gcta, and there are polygenic scores, which I call POGs. More often said PGS, but I will call them POGs. These are the three things going on. And then those of us who come from the statistical side and are trying to keep up with the developments there's been huge waves of applications. I saw some pictures of the number of GWAS studies, 2,000, 4,000. Did you put up the slide? Dan? Anyway, thousands of papers. No one in this room has read them all. Gcta took off in 2010, and there are many hundreds of papers out there now. No one in this room has read them all. I venture to say that none of the authors of these papers have read all the papers of which they are the authors. This is very big science enterprise now, and polygenic scores have now taken off in the last few years, and even to read one of these papers, the papers add up to hundreds of pages in supplementary information, and again, they are taking over the world. One can't possibly, if you're like me, read what's being written. And again, I doubt that most of the authors of each of these they're great papers, I doubt that most of the authors have actually read the whole of the paper of which they are an author. It's a lot of division of labor and so forth, but still, these are big games out there. Those of us who come from a more mathematical and statistical and demographic side look at this, and as we struggle to read one or two of these 300-page papers, come to the conclusion that the applications have far outrun our understanding of the statistical properties of the methods. There is software out there. You can run the software without having any idea what's inside it, and the practitioners come, happily driven by medical and social science substantive concerns, and they collaborate some with statisticians along the way, but the payoffs have been to get the substantive results out, and when people like myself come and look at them, we have a sense that they're doing all kinds of things that, on a statistical side, that are not really understood. And in this field, because it's become hot and wonderful, as Kathy said this morning, there's a huge impulse to go chasing the next shining thing. So the fear is that before we understand what any of these methods are doing, we'll be doing something else entirely. It'll be microbiome, or it'll be the epigenetics, or many of the things that Tolja talked about. They're already out there, and before it even gets to being able to write down the actual model, the world will move on, and there will be 1,000 studies in the literature making important substantive claims that may or may not be right, but no one really understands and will have forgotten the methods that went into them. And I have the feeling that this has already happened once in this field. When one looks at the long tradition of estimates of heritability from twin studies, which became a whole somewhat ingrown academic world, and when iconoclastic economists started to look at twin study estimates of heritability, they became very doubtful. And I think that after maybe 20 or 30 years of work in twin studies, the whole field is now dodgy, dicey. And when one talks about the hidden heritability question, one rarely says, well, the heritabilities have been established by twin studies. We now more often hear, well, maybe the problem is that the twin studies got it wrong. They overestimated heritabilities because of the design problems that economists and others have pressed. And so one would hope that in meetings like this we can get enough ahead of some of these statistical, methodological claims so we don't do that again, so that we don't have a large, wonderful enterprise that when new approaches and new technology come down the line, people tend to just say, well, maybe. Now, so, what are the technical issues that are on the table this afternoon? These are largely around Gcta, but very soon the same things are going to be starting to ask about POCs, about the polygenic scores. So there is a dispute now, an important dispute, about whether in the cases when its pure assumptions are satisfied, when in the best case scenarios, what I like to call simple Gcta, whether the heritability estimates are biased and biased upward. Many people, myself included, believe that most twin study estimates of heritability have been biased upward, and Gcta is coming up with lower estimates. Most of us, many of us, I think, more willing to accept, but Sid and David and Toljan and Mark and they want to raise the question, are Gcta estimates still biased upward?
I don't mean to interrupt, but before you get into before you keep going, can I ask a question about what you just said? Because
well, I think I'd like to introduce the whole
okay.
Introduce and then come back, because I only have 3 more things to say. So why don't I say them and then? So there is a technical question being debated among the people here who are together and talking about this. David and Andy and I believe that the answer to the systematic bias question in the simple setting where the assumptions are satisfied, that those estimates are not biased in that simple setting. And I think there is a hope to convince those are asserting bias. So this is one of the small claims in the paper under discussion. Not a small claim, but one of 5 or 6 important claims in that paper. And I would hope that that question can be settled among the participants as to whether there is bias in heritability estimates in simple Gcta when all the assumptions are satisfied. So that's a point of contention that in all the equations that you saw up there is being described about. I think that the teams that are looking at this are all agreeing on the importance of variance where sample sizes are small. So much of what Sid was presenting today, and David talked about TAW2, essentially variance. I think there's now large agreement that the variability in GCT estimates can be serious in not 500,000 size samples, but in samples that many people are working. I think that's a point of agreement, but if that point can be hammered down, that is valuable too. And then the negative heritability, resulting bias, is another important area where I see that there is agreement coming. My sense is that most of the people in this room will say, keep those negatives. If there's agreement, that's important to hear. But the big issue in these bias and variance discussions is how much is GCTA ultimately exploiting population stratification from deep ancestry. They exclude known relatives and close connections, but there is structure of deep ancestry, and those who talk about these eigenvalues and singular values, all of that is about how much of the variability that genome-wide methods are using is reflecting not independent samples from a homogeneous population, but structure built in over thousands of generations of deep ancestry. A lot of what the GCTA studies have brought up is the strong difference between these quantities, the singular values, that one would expect from truly independent draws from a homogeneous population, whose distribution is well known and long studied, from the actual singular values that one sees in these different samples that Sid showed us and David showed us. So this question is going to come up with POGs too, because despite on the face of it, arguments that polygenic scores are not picking up stratification within family studies that encourage us to think it's not stratification. There's a lot of arguments out there. People have been very careful about this, and yet I'm not yet convinced, because the singular values of the genotype matrix suggest that there is a lot of deep stratified structure. And so this relates ultimately then to the trouble with twin studies, which was that shared genetics was confounded with shared environment to the extent that GCTA and polygenic scores are tapping into some form of deep population stratification. There is a possible confounding between what we're calling genetics and what the genetic markers are telling us about people's ancestral history. So this issue of the prominence and role of stratification is, I think, a crucial one, and that's an issue that you don't have to be a technophile over here to talk about. How far are we really getting outside of population stratification of subgroups? Right? It's not the fact that skin color genes affect anything, it's the fact that they mark something. Not the fact that dropping H's or articulating H's means something. You might have a genetic effect for it. It's marking something. And the same thing comes back in these, what we mean by causal markers. Are these causal markers that are causal over evolutionary time, doing something at the molecular level to our cells and to the aging and capacities, or are these causal in the sense of picking up something that is marked by genetics about our present-day environment? So these issues, though they sound very technical, are not just technical. They are essentially about the nature of social science genetics, about the nature of heritability. And settling some of these points now, and not 10 years from now when outside critics come to look at the work we've all been doing, seems to me important. So this is, I hope, a valuable meeting in that sense of tackling these issues, not just running toward the next new thing. So that's my background for why I think this is important. Let's open discussion, and do you want to start then?
Sure. So I
and please speak loudly. I'm quite hearing impaired.
So I was struck by your initial remarks about characterizing the twin studies. Behavioral genetics, twin-based research community seems to be like a model of what not to do in the subfield in terms of being cloistered and resistant to criticism from outside and so forth, and self-reproducing over 4 decades, very marginal contributions with a number of problematic assumptions. Yet, at the same time, my reading of the literature on additive heritability using a variety of approaches was that despite all of that, actually twin estimates are not bad. That the adoption studies with random assignment that economists have done, there's reasons that Gcta gives you an underestimate compared to the twin models, and so forth. So I'm very curious. My first question, number one, is how you got a different reading of the ultimate sort of status of heritability estimates being way overestimated. I would love them to be overestimated. I went into this field as a social scientist wanting to show that they're overestimated and feeling like I failed. The second thing I just wanted to raise was I find it really fascinating that Gcta, or Gremel, or what you want to call it, has exploded in terms of exactly the way you said over the last 5 to 7 years or whatever it's been. And there's an earlier paper by the same group, the Yang Vischer folks, called in PLOS Genetics, I think 2007, Assumption-Free Heritability Estimates that uses sibling IVD approach. And it's not assumption-free. I'm going to talk about this stuff tomorrow morning, but I think it's better than Gcta. And I get that one of the limitations that why that hasn't exploded in the same way is that it requires sibling data, which are not as common in the medical cohorts and so forth. But there's certainly still a number of data sets, including AdHealth, including Swedish Twin Registry, Minnesota, the Queensland group, the ones in the UK. There's, you could put together a consortium of at least probably 10 decent cohorts with sibling data, and yet that approach hasn't taken off. And I've always been curious. I don't know if this is the right group to ask, but why not? And third comment is that I think there's 2 separate issues here about the deep ancestry, which I also will talk about tomorrow morning. I agree 100%. There's confounding with ancestry, even after controlling for PCs using Gremel. But the skin color example is interesting because even if you do the sibling fixed effects on a PGS for education, let's say, which by definition, or on a single allele, or any sort of genotypic measure, or any haplotype, you're going to get that should break the confounding with ancestral environment, and you can get estimates. But in the skin color example, it still doesn't tell us what still could be a mechanism that Within families, skin tone varies genetically, randomly assigned at conception, but the mechanism is something that we don't feel right calling a genetic effect. I mean, when I talk to other sociologists, this example is the one that always confounds, because we know it's a form of quote-unquote illegitimate bias, but it is 100% a genetic, so the behavioral geneticist would say that's a genetic effect. That's part of additive heritability. There's no problem with that, even though it doesn't strike us as something we want to estimate or consider part of the estimate. But that's different, I think, than confounding by ancestry. I mean, the society is confounded by ancestry. The assignment of the alleles is not in that case. And I don't know if there's meaning. The reason that skin color is an effect is because of history and the environment of history. But but you can solve within family analysis. You can solve the problem of the confounding on the right-hand side. I don't know how to think through that distinction, but I think that's an important distinction versus people living in the north and the south of the Netherlands that have different genetic signatures and different environments because they're living in the north and the south of the Netherlands. That makes sense.
Can we encourage you to say something? So, on the urban-rural.
Sorry?
Snip, Gcta for urban and rural.
Right.
Can we encourage you to say something on that?
Well,
So all kinds of things that shouldn't be genetic turn, as you and others are showing us, turn out to be predictable. So perhaps I shouldn't have muddied the waters with the skin color, but you can can you say something about many things turn on here that are better illustrations?
Yeah, basically, even when you can control for 25 PCs, and there's two things. There's still residual correlation between the chromosomes, the relatedness by chromosome, which violates their core assumption that the different, at this very low level of relatedness, that any similarity is actually due to the randomness of recombination, because then it should be completely independent by chromosome. Jeremy and I could be more related to chromosome 8, but then Ben and I would be more related to chromosome 7, but there seems to be a weak structure still persistent even after controls for PCs. Now I'm really giving my talk for tomorrow. And it seems to generate heritabilities for things that we think may have a very small genetic component that maybe I inherited a preference for urban living from my parents, but that's removed. Even if it is slightly heritable, we're talking about kids growing up and they're only 50% related to parents, so it should really be only 25% heritable, whatever the heritable coefficient is, and we're finding much bigger Gcta estimates for that. So that suggests that there is some biasing coming from this deep ancestry that you're talking about.
I'm confused about deep ancestry, I think, because it wouldn't occur to me to question the heritability of urban versus rural residents, first of all. And this is in the United States, right? You're looking at the HRS.
That's the point. We're taking something from childhood, a childhood environment.
Yeah.
That should, yes, parents might, where I choose to live might be heritable, but we would think they should be significantly less heritable than, say, education level or cognitive ability or the things that we think of as at 0.2 in GCTA. Education's 0.2. We're getting almost 0.2 for urban-rural.
Yeah, I'm not. I guess I don't share the assumptions there, but that may be neither here nor there. I mean, I think if we've learned anything from sort of 40 years of doing twin studies of this same kind over and over and over again, it's that everything under the sun is heritable, and that when we now have molecular genetic tools to try and investigate the extent to which that might be an artifact of some feature of the twin study, we see that it's not purely artifactual. I mean, I put up data today suggesting that this, sort of vague genetic signature revealed by doing GWAS of educational attainment is related to all kinds of features of people's lives and choices that they make across that lifespan.
And more importantly, not others.
That's true, and it's specific.
Yeah, exactly.
My guess is we'll begin to see more and more of this as GWAS moves out of the sort of cloister of biomedical case control designs and into population samples. But
so
I think...
Can I just ask, so is the claim that you're making is that, so you believe it is reasonable to assume that the tendency of rural people to be more related to other rural people could be explained by effects coming because they have certain gene variants.
So
that would be at least that would be a plausible explanation.
Right. So greater genetic similarity of rural dwellers to other rural dwellers and of urban dwellers to other urban dwellers could be driven by preferences, traits, and behaviors that are influenced by common genetic variants. I think that's the claim. Yeah. So with respect to deep ancestry, though, the idea here is that this deep ancestry is driving both genetic similarity at the genome-wide level and similarity in environmental contexts that are causally independent of those genetics.
Well, I think that's
the claim.
The alternative.
That's the alternative, yes.
Okay.
So, for instance, I mean, one could make a story that there's been a certain pattern of settlement in the United States which led certain clusters of genes to be common among rural residents in a way that you could not identify by any particular relatedness.
But that's entirely accidental. The point is that those genotypes play no role in the selective survival or residence of individuals in those rural locations. So, for example, genes that make one better able to survive under certain conditions versus others that bias toward rural residents, let's say, are excluded. That's not what we're talking about here.
That would be yet a third kind of explanation.
Well, I think that's the first kind of explanation. So the idea is that we don't know what the genes in these polygenic... Just so clear, there are two stories here, right? One story is that genes drive traits, behaviors, characteristics that form environments, right? That select individuals into one place or another, lead them to have a disease or another. And the other is that accidents of history lead genetically related people to find themselves in environments that are themselves causal of the diseases that we then misattribute to these genetics.
That's the bigger concern.
I think the problem is that it's both are going on, and it's hellishly hard to tell one from the other.
My point was that if you're talking about where I choose to live, urban or rural, which would be, I think the first one where I'm selecting the environment as part of the genetic effect with, migration or residential choices as an endogenous environmental pathway to whatever outcome I'm interested in. Then maybe 0.2 heritability is plausible, but seems to me pretty high. But then if you're asking about my childhood, which I had no control over where we live, so the only way that that first story works is that my parents, who are genetically related to me, made a share of the genes and made the same choices. But then,
and who probably assortatively made it on some of those same preferences, right? So
sure, but still, I would think that you should expect. Well, what do you think is a reasonable heritability for that? Then?
What the discussion this afternoon persuaded me of more than anything else, and this is, I guess, consistent with other things that have been written about heritability, is that heritabilities are not well estimated. that they're contingent on the structure of variance in the population that's being analyzed, that everything is heritable to an extent. If you get estimates that are extremely high, they're suspicious. If you get them that are extremely low, you've probably poorly measured your dependent variable. So 0.2 or 0.4, the confidence intervals are generally extremely large, and that's certainly true in twin studies. I don't know that we urban and rural is measured highly precisely.
Height is more heritable than educational attainment, which is more heritable than something else. I think we have to have some structured priors. We think that height in a nutritionally rich environment is less environmentally biased. I mean, this is again part of what I talked about tomorrow, but less environmentally biased than, or potentially environmentally biased by deep ancestry than depression or education or some psychosocial outcome would be. Not in Zimbabwe, but in the United States.
I think it's better measured than those things. I'm not with you that it's a priori more heritable. That genes play a stronger role in height than they do in other complex human traits. At least I don't know that we have strong evidence to that effect.
Okay, well I would, whatever.
That may be an extreme position.
If we don't know that, then I think we should all just go home.
What about, there was also an issue of whether I'm misrepresenting or just putting out my own prejudices about twin studies, or how other people who know much more about this feel about that, and along with articulating the debate we just heard. What are the views about overestimates or not of heritabilities?
So,
are there?
Go for it. Oh.
Kathy, you're typing notes, but you've set up, run this large design which to some extent integrates the sibling, twin, and genome-wide perspectives. Do you have a view? From hearing your panels and everyone who report to you about what you should be studying, what's your sense of the state of belief around?
Well, that's what I presented was sort of that, the unfolding of the history in the integration of genetics and social science. And so we started with that embedded genetic design because that's all there was at that point was, these sibling types of models. And I had it up on my slides. I've sort of bought. I agree that. Actually, I'm getting a new appreciation for for these types of models. But I felt like the heritability estimates, the ranges, were so wide that you could have picked. You could have picked almost anything. And I figured that what mattered was the types of samples that these estimates were coming from. So that hasn't been brought up, but up until the time that Ad Health drew your sample, I don't think any. Well, I guess we did have some national registries of twins, but most of the samples were not representative and sort of convenient samples and specific ages and whatnot. So that might have been part of what was behind the range. But then, over time, as molecular, just like Dan said, as molecular data became available, then we were able to, to test some of the assumptions. But yeah, I basically think that the original sort of behavioral genetics models were, gave us the wrong results.
I would agree with that. I think that there's, I haven't kept up with the twin study literature in maybe the last 15 or so years, except, selected parts of it. And I've never been, so the earlier stuff,
really had very cavalier treatment of environmental effects. Secondly, we've all tended to use some form of an additive statistical model. And, it's been known for a long, long time that all you're doing there is you're making a local approximation to some kind of nonlinear relationship. So if you think about, what deep time is doing, culture is framing our perception of environment. So for example, you had a test, which was this Wechsler test, and to us now it seems like a reasonable instrument, but I think it's an instrument that 50 years ago may or may not have existed, and there was probably very different, I don't know, but certainly 50 years ago there was a lot of debate about this, 25 years ago. And probably 25 years from now we'll have, very different sort of instruments that we want to use, different ages at which we think it's important to measure intelligence. There's a lot of evidence that even with linear additive kinds of models, its heritability changes with age. It doesn't always do so in the way that you would think. It can increase with age. It changes with time. It changes with cohorts. It's just kind of a moving target. So to me, when you talk about, say, the skin color thing, for example, biology definitely plays a role in skin color. It's not entirely clear to me that we understand the biological mechanisms perfectly, but we certainly do have some sense that, there's a strong association here. But does it matter? And there, I've got a colleague who is an anthropologist at Tokyo who has traced, the fitness effect as measured by your likelihood of finding a spouse, of being relatively fair compared to the background coloration back about 7 centuries. So you have strong cultural expectations across the globe, where people say, you should be this color and not that. So I think then, you've got intermarriage and selection of mates and whatnot. So I think the final thing I'd say is you say, well, I ought to have some strong prior about heritability. And I don't actually. I think Ben said it nicely at some meeting we had. He said, the heritability of the number of fingers and toes you've got is 1. But it's 1 or 0, as you wish. But, aside from those limits, but it might be, I think it's 1 actually. And I think the reason I think it's 1 is because in embryogenesis and very early intrauterine development, if you have an embryo that is going to form with 11 fingers, its fitness is 0. The survival rate in the very early stages, I don't know at what stage, but somewhere between, conception and a lot of these kinds of genetic effects that would produce embryos that have, all kinds of body plan problems, have that effect. So that's part of the context in which I think about this question of relatedness, which I look forward to being illuminated on tomorrow, is, we have both constraints and evolution, and that's not clear to me how they play out.
Heritability as a ratio or as a correlation is one thing, but in the popular or the broad scientific drive, it's really genetic variance. Is there genetic variance? Are there causal relationships that you would have from measuring our 39 million Snips for a person. So what you're dividing by as phenotypic variance is historically important and practically important, but not, I think, the deep substantive issue. It's surely not true that there are 39 million genetic variants that each have causal influences on the physiology of individuals. Much variation must be neutral from a biological,
With respect to a specific trait.
With respect to specific traits, yes. And so there is this notion of, but wholly neutral sites inform us about history. Mostly inform us about ancestral history. So there have to be a fair portion of our data that is accessing ultimately very complicated pieces of history over thousands, tens of thousands, hundreds of thousands, and millions of years of history that may do nothing biological, or nothing that we have a glimmering of yet biological. And so it does seem to me that this debate is out there in our minds, independent of the specific measures of heritability. And I guess perhaps by not knowing enough to be better informed, I certainly come in with prejudices about how much some traits could be turn out to be driven by these neutral sites, and how much others are less likely. I have these priors. Are they all prejudice, or are they informed? I found it very surprising when this the study of the urban-rural residents of children came out. I certainly had that prior, maybe from poor information or from leading information, but these priors float around in our heads. Do you manage to keep them out of your head, or?
I think I just have different priors. I think, yeah. I mean, I don't know the specific biology of any of the variants that we study, really, or any of the traits that we're looking at. But it is the case that human traits and behaviors are highly heritable, and that measured heritability is often proportional to the precision of the measurement of the trait in the given study, conditional on sort of how big of an effect specific environments have and what their frequency are in the data sets that we study. But beyond that, we just don't know very much about why people do what they do, except that they're very good at doing it despite our best efforts to the contrary. And I think, if you want an explanation for high heritability coefficients, or you want evidence of high heritability coefficients, why is it so hard to change people's behavior? Because they've ended up built in a certain way to do a certain thing. And that's not exclusively a genetic effect that occurs independent of any environment, right? The heritability coefficients we estimate are the sum total of pure genetic effects and any interaction that genes have with any environment that's shared by more similar people, and given all the evidence for gene-environment correlation, they share a lot of environments. So that's a whole lot of stuff, but
but we typically don't have good measure. Oh, sorry. Okay, go ahead.
Well, I just want to say, I think an important part of the story, which is often forgotten, and I think this explains why some of us have an expectation of low heritability, is that heritability is a ratio, and if you know that there are major non-genetic causes of variability in a certain trait, so for instance where you live it might be that it's driven by, that you have an inbuilt preference for the color green, and so you live in a rural environment, right, or whatever it is, right? There could be, these modifications which tune your expectations in a certain way, and your appreciation of noise, all these things which could drive you in a certain direction. But this is operating within an environment where people move to a place for work, and because their grandparents own a farm, and all of these things. So, when you come into a situation where just as if you know that a significant part of the population is undernourished and is therefore short, you would be very surprised to find that you found a high heritability in that population for height. And
unless height, the genetics are regulating to what extent the malnourishment determines your height, right? Genetic heterogeneity, in the face of an environmental stimulus, goes to heritability.
Yes, but the point is, if there is a substantial variability which is purely due to how much nutrition you have, then the plus or minus of that is not good. All I'm saying is, if you know that there are random or cultural or familial
Sources.
influences, then yes, it would be surprising if genetic variants are going to create a large part of the variance.
Another way to put it, sorry, Dan, is like if you have two kids, right? If you wanted to control, you want to control their height, you want to structure the environment as much as you can. Good luck.
But let's say you have two kids, and then you sort of systematically undernourish the pair of them. You're going to get different height outcomes for those two kids. The differences in those height outcomes are going to be partly genetic, and that variance is going to go to heritability.
How much do you see that within families in the United States today?
What you see instead is a common nutritional environment that's not undernutrition. It's these days more likely overnutrition.
But if I'm getting the same IBD heritability within family analysis as I'm getting from a Gcta or twin study or whatever for height, and it's higher than everything else, doesn't that suggest that either that's biased too, in that parents are doing crazy experiments like you and me and malnourishing one of their kids, or in this environment, there's not a lot of environmental variability, period. And it's mostly genetic variability that's expressing itself. I don't think you have a much more open mind than I do, I guess.
About potential genetic influences.
There's no prior that height is more heritable than, let's say, mental health.
The height.
Well-being.
There may be more pure. There may be less G by E, let's say, in determining height in today's sort of world than there is G by E determining depression variance. But I think that how people react, we all see tremendous heterogeneity in the way people react to stress, right? So some people develop symptoms of depression and others don't. Some people's symptoms of depression abate in short order, others don't. The variance in that response is partly genetic in nature. And so it may be that there's a lot more G by E in depression variance in the modern population than there is G by E in height variance in the modern population. But that all contributes to heritability.
But it doesn't have to be genetic. You could just do. You and I could both go play the slots for 20 minutes, and I'd lose my shirt, and you'd walk away a winner. But it's got nothing to do with genes, which the variances in the outcomes are huge. So the total variance.
So heritability of slot performance? You're right. I have a strong prior that the heritability of slot machine performance on a night at the casino should be extremely low.
I will bet you that if you did an analysis with any of the techniques that we now have about the heritability of slot performance, you will get 0.3. I guarantee you.
You don't have to convince me not to trust heritability.
I've seen thousands of these estimates published, and every time they do it, they just do it until they get at least 0.3. It's a long major.
So one thing that's bothering me in this, and I want to use the urban-rural example, is that there's a secular trend going on in a lot of these social phenotypes we're talking about. If you want to talk about heritability of being urban-rural, the variability there has gone down. Because, I mean, I don't know the study to which people are alluding, but if we're talking about people over a reasonable time span, you know, the U.S. population, because we were all here, was more than 50% urban, in the early 20th century. So, you know, that's when the variability in urban-rural living circumstances peaked, and it's gone nothing but downhill since then. People were just less variable in where we live. And I don't know what the exact implication is for heritability off the top of my head, but it seems like that's going to greatly confound our heritability estimates of living in an urban or a rural place. I suspect if we were to look at fertility, we would see something similar. There's a secular trend of people choosing to have fewer children, and that's therefore the variance in how many children people have is probably going down. And if we're going to talk about the heritability of how many children you have, you somehow need to account for that secular trend. And I don't think in the variance itself, not the mean, and I don't think we're accounting for that in any of these estimates.
So one thing, so when I started working on some of this stuff, I heard statements of the form, well, the heritability estimate is 0.61 or something like this all the time. And this statement is completely meaningless to me because it's not a fixed number. You know, you can't just say independent of itself, the estimate is 0.61. And that was one of the reasons why I started looking at this stuff, because I was like, well, you can't look at just looking at an estimate is like life expectancy is going up. Statements like this don't make much sense unless you look at the standard errors around them. And most of these things, the standard errors are so huge that I think it's pretty fair to say that we don't know anything about them. You know, would you venture something different, or?
Well, we have two different things on the table. One is heritability, which is this ratio, and everything that's being said about background variance affects that ratio. The other is about causal alleles that have predictive power, of which we find very few that we can put, very few, but increasing numbers on which we can put names on, but in which from Gcta and from polygenic scores, we have evidence that there are quite a lot. And so there's there's the ratio questions we're talking about. That's where the subject has been. And I don't hear too much disagreement around the ratio issue. But then there's the causal versus marker interpretations of what is being measured. And that seems to me that that's a debate that lives independent of the particular measures you pick. So who else was on? No?
I was going to, sorry.
No, go ahead.
I was just going to ask a question because I don't know. You know, is there evidence from animal models where you can, you know the complete ancestry, but you can manipulate the environment that tells us anything?
Well, so it's related to the point I was making, which is if you look at breeding programs, they do estimate heritability. They do have decent pedigrees, and they have achieved striking results, but their predictability is poor because they don't understand why they get correlated responses and things. And you get very startling responses. So you can breed, one example is you can breed broiler chickens and, for their appropriate fat to lean ratio and size and efficiency at converting grain into meat. But certain selection programs produced chickens that were extremely violent and that pecked each other to death. This was not a good outcome. So then they tried another selection regime, and that, and with plants, for example, in fact, in general, with many of these programs, The other problem we run into is that heritability, one way of thinking about heritability is that it tells you how responsive you are going to be to selection. And that doesn't actually work. It works, when it works, it's great. And when it doesn't work, we haven't the faintest idea why. And a good example of that is that you can select on plants. And there have been lots and lots of studies on plants, fruit flies, all kinds of things. You do selection, you get a response, and then it just plateaus. And they have absolutely no idea, because what's happening is that there is genetic variation, but it's being locked into place in such a way that you simply can't budge it. And so the way they budge it then is you change the nature of selection, you start selecting on something else, and maybe with luck you break out. But then you can go the wrong way on the target trait. So, Dalton, and then Martin.
I just was going to say, one, the more depressed, I mean, there's all the estimation issues, but I think why do we care about breeder's coefficient in humans? I mean, I can say why, there are people at 23andMe and other places that do really care because they want to breed humans to select for higher intelligence. There's some very rich people out there funding this stuff. Embryonic selection, but also mate selection and so forth. I mean, they do want to do this. But why? That's the question that gets me more depressed of why I'm even doing this. Why are we doing this? Why do we care what H squared is, and what do we? And even if we have a PGS, that predicts, and we don't know the pathways. So what do we care about that either?
That's the thing. You're much better breeding on observed traits than measured genotypes. You get there a lot faster.
Ron?
So, I may have completely misunderstood many things, but my impression is that all of these three approaches we've been talking about are all linear. They're sort of in the category of linear approximations that you mentioned, Tolja. That's what I really don't understand, because I thought a lot of the stories were about the effects of the presence of multiple genes, or at least one something that turns on something else. And if the something else isn't there, that won't have an important effect. And if the switch isn't there, that won't have, the original thing won't have an important effect, and so on. And so is it possible, when such small heritability factors are found, that it's because we're only looking at additive effects of things one at a time? I mean, this is, so much work has been done and so many people have thought about this, I can't believe that. Anyway, I don't know how to think about it.
So can I interject? So additivity is a statistical solution, right? Because the non-additivity is of an unspecified nature, it'd be really hard to model. But there's also some sort of strong biological theory about why we should have additive relationships between genetic variants and phenotypes, and that's because when chromosomes get together and swap their bits, they don't do it in a coordinated ballet, at least so far as we know. There are recombination hotspots, so there are some points along the chromosome where you're more likely to get recombination than others, but in general, you're inheriting bits of genome from mom and bits of genome from dad, and if we had complex epistasis across large expanses of chromosomal space, we'd get failure a lot of the time, because you'd end up with the wrong bit. You get a non-compatible bit from mom and dad. So he's a physicist, actually, Steve Su. He's the vice provost of research at Michigan State University, and I guess he said some things that make him more radioactive than the rest of this discussion. But he's a terrific writer on the subject of complex genetics and this additivity issue. And he has a great quote in which he says, biology is the additive, or the linear combination of nonlinear gadgets. So at the level of molecular biology, it's all interactions the whole way down. That's absolutely right. So when we can sort of observe cellular processes, we see gene-gene interactions right and left. But those are interactions between bits that are working together, right? That we shouldn't see necessarily.
Together? That are inherited from one or the other of your parents together?
Often in which, so it's often not variation in genotype, right? So the gene-gene interactions that are being observed are interactions in the effects of genes, not necessarily epistatic effects driven by different alleles at a given genetic loci here, and then different alleles at a given genetic loci there. So the nonlinear gadgets have to be inherited whole, right? And then the linear combination occurs because that's essentially the process of mixing of genomes that we get in reproduction.
I do want to point out that you say that we can't have this massive amounts of epistasis because otherwise we'd fail. We fail a lot. I think the good statistics are hard to come by, but I think
we all die.
Well, beyond the 100% mortality rate, I mean like at conception. From there to birth, a quarter of all conceptions. 70%.
So
we fail a lot.
Sure. That's genetic variation that doesn't show up in the population to drive phenotypic variation, though, right?
Yeah.
Well, only those particular combinations of the alleles, but the alleles themselves are clearly still around.
Would look very different if there was huge epistasis, because they'd be inherited linearly 50%. But just imagine if you have four-way interaction that's usually significant for height, basically siblings would not resemble each other effectively in height.
Yeah, so the additivity
but it is the case in the twin studies. You're getting the whole genome with all those multi-genomic gene interactions, whereas in this analysis, you're not.
In the MZ twins, in the DZ twins, you're still getting DZ twins. If epistasis was hugely significant and mattered, then DZ twins should not. They should have way lower than 0.5 correlation, even just taking away environmental effects. But they don't.
But this is a very good point about the amount of genome that's measured in a biometric analysis compared to a Gcta or even LD score regression SNP analysis, right? Where you observe the complete genome, rare variants and all, microsatellites, VNTRs, SNPs, etc., as opposed to SNPs, and not that many of them, right? A couple of million, and whatever they tag. And so this issue of imperfect linkage may be part of the answer to the conundrum you've raised about how can so many sites on the genome be related to so many different traits. And part of, I think, what we're getting, the reason that you expand your predictive power by including more genetic information is that many different variants are bad proxies for a common causal variant. And the more bad proxies you line up in a row, the stronger your resolution on the genotype of the unmeasured causal variant is. It could be one reason that, well, it's a longer discussion anyway. I think that's something to consider.
Okay, I think we'll call it a day. Everybody's tired? I am. So we start at 8 tomorrow.